the Kepler's laws of planetary motion. In the previous lecture, I told you that we can handle the gravitational force or the problems of the gravitation by using the Newton's law of gravitation. There is another approach, and this is done with the help of Kepler's laws. Here I would like to point one very interesting thing. See, we have so many objections for the Newton's law of gravitation, especially when we deal with the heavenly bodies. People have a doubt that is it the gravitational force is inversely proportional to the square of the separation? Is it that the power is exactly 2? There are certain cases where we find that this is not true. There are certain objections in the Newton's law of gravitation, but still we are not able to find out even a single objection for the Kepler's laws of planetary motion. One can always derive the Newton's law of gravitation from the Kepler's laws of planetary motion. These laws are true laws of gravitation, in fact, and you can treat the Newton's law of gravitation as a special case of the Kepler's laws. With this note, let's understand what are these Kepler's laws of planetary motion. When a planet is revolving around the sun, say the planet is revolving around the sun, according to the Kepler's first law, the path is always an ellipse and the path is elliptical path. Here I would like to mention one thing. Circle is the special case of ellipse, right? In the previous lecture, I discussed with you satellite revolving around Earth, and in all those cases I took the path, circular path. In general, the path is elliptical. As a special case, it can be circular if we need it. This is the first law, is a straightforward law, and this Kepler actually observed the motion of the Mars, and from the very accurate calculation he reached to the conclusion that the path is not circular, path is elliptical. The second important thing is, or second law is regarding the position vector from the sun to the planet. Let's understand this more in detail. Sun is located not at the center, but at one of the focus point of the ellipse. If I join a line that is joining the center of the sun and the center of the planet, we call this as in the same time, anywhere in the ellipse, say the planet is somewhere here at P3, and for the same time it reaches to a new position, say P4, and if one calculates this area, these two areas are exactly equal. It means if this area is A, this area is going to be A. In words, one can say the radius vector sweeps equal area in the equal interval of time. There is another way of saying it, and that is the aerial velocity dA by dt, that is the area covered in time dt, always remains constant. This law is based on one of the very important law, that is the law of conservation of angular momentum. Angular momentum L remains constant during the motion. Do you remember I told you that Gravitational force is the central force. That means when this planet experiences a force towards the sun, this is always along the line joining the planet to the center of the sun. What I mean by this is, if you take the planet position somewhere here at P, and this is the line which is joining the two centers, the force experienced by the planet is always along this line. The position vector is always taken from the center to the planet, and the angle between the two becomes 180 degree. So the torque, which is given as Rf sine of theta, in our case, since theta is 180 degree and sine 180 degree is 0, so torque becomes 0. It means planet is not experiencing any torque because of the gravitational force. If it is not experiencing a torque, then from the law of conservation of angular momentum, the angular momentum dl by dt, that is 0. Angular momentum rate of change is 0, that is torque, which means the angular momentum will remain conserved or constant. This law is in fact based on the law of conservation of angular momentum. I hope everybody remembers that angular momentum is directly proportional to the aerial velocity. That is the geometrical interpretation of the angular momentum. Since angular momentum is constant, so the aerial velocity remains constant. So they are linked together. So this is a very important law. At this stage, I would like to mention some of the mathematical relation which you should not forget, especially for the elliptical path. If we have elliptical path, then this is the major axis. This is the center of the ellipse. Let me put this as O. This is the position of the focus point F. There are two focus points, one on this side, other on this side. This distance is normally represented as C. And from the center to this end, we normally call this as semi-major axis A. A is semi-major axis. C is the focus distance. There is another side which is perpendicular to the major axis. This is the minor axis, but half of it is called the semi-minor axis. This ratio C by A is normally called eccentricity. Eccentricity. And eccentricity for ellipse is always less than 1. Less than 1. The moment it becomes 0, the shape of this ellipse is circle as a special case. So sometime they are asking the information in terms of the eccentricity. So this mathematical term is required while handling the problem of the motion of planet around the sun. There is another interesting thing. That is, when planet is revolving around the sun, in order to keep the angular momentum constant, when the planet is closest to the sun, it is moving with the maximum velocity, and this distance is r minimum, and at this position the angle is 90. When planet is at the farthest point, it is going with the minimum velocity because the distance is maximum. Once again, the concept is related to the angular momentum. As you know, angular momentum is mvr sine of theta. Since angle is 90, sine 90 is 1, so one can write m v max r minimum is equals to m v minimum r maximum. You can remove. So we can write V maximum V minimum is equals to R maximum to R minimum. So this is the interlinked relation. Once again, in the same way that the angular momentum is constant is a result of that. But if one tries to write the R maximum, look, from here to here the distance is F, right? Or you write this as C. And from this to this the distance is A. So I can write the maximum distance as A plus C. But this distance, which is R minimum, the whole is A, this is C. So remaining distance will be equals to A minus C. So this is A minus C. Now if I divide numerator and denominator by A, I get this as dividing A by A means 1, C by A, 1 minus C by A. And C by A is nothing but is eccentricity. So I'm getting one relation which is of extreme help, that we get the V maximum to V minimum. 1 plus eccentricity divided by 1 minus eccentricity. So these are all related to the second law of Kepler or planetary motion. So these are some of the details which you should remember. They'll help you to solve the problems. Now with this we come to the third law of Kepler, which is very useful from the question point of view. Next slide, sir. Third law is a direct statement regarding the time of revolution. Capital T is the time of revolution of a planet around the sun. A is the semi-major axis. So the law says that the square of this time of revolution is directly proportional to the cube of the semi-major axis. If the path is circle, the semi-major axis is equal to the radius. So you may say that this is T square proportional to R cube. Most of the time the question which are asked from this section, they are comparative type of questions. They'll give you that there is an object which is revolving around a planet, which is a system equivalent to the sun planet system, having a time period T. They will give you the radius. They'll say there is another object with a different radius. What will be its time period, or if time period is given, what will be its distance? So what all you have to do is you have to write the relation for both. That means if I take an example that this is a planet, say of mass m, and this is one satellite, say of mass small m, revolving in a circular path of radius, say r1. Similarly, there is another planet which is revolving around this planet in a radius r2, and I have to find out a relation between the time of revolution of one and time of revolution for the other planet. You can handle it very easily by using the Kepler's third law, writing the equation, first equation for the first planet, that is T1 square proportional to R1 cube, and T2 square proportional to R2 cube, and then you can divide the two. T1 divided by T2 whole square is equals to R1 by R2 whole cube. The constant of proportionality here and constant of proportionality here, they will be out from the scene, and you can directly have a relation between the two. So this is how this is used. There is a precaution which you should keep in mind. Sometimes what they do like this. They say, okay, the radius of this planet is R, and height of the satellite for the first case is h1, and height for the second case is h2. Then the same relation will be taken as R plus h1 and R plus h2 whole cube. It's one same thing. So we have a very careful eye on the language of the question. Are they giving the radius or they giving the height of that planet? Radius we are able to take because this path is circular. Had it been an elliptical path, we have taken the semi-major axis in this case to get the thing. And when you just use this one, T1 by T2 is equals to R1 divided by R2, 3 by 2. Power is 3 by 2. And I hope everybody knows how to handle it. It means that you take the cube of this number first and then take its under root. So this is how these type of the questions are handled. But now, as I promised that we'll discuss about the gravitational flux, I'm taking this understanding of the flux in detail, right? Today, before we come to the question. In my previous lecture, we understood few things. Let's quickly revise those things. If there is a mass, we can always talk about what we call as gravitational field lines which are approaching towards the mass. Like this. These are the gravitational field lines. The second thing which we discussed was what is called the gravitational flux. This was nothing but the surface integral of gravitational field taken like this. You can use the symbol capital E also, or you can use small g. This is your choice. This is the gravitational field intensity and this is the surface element. The meaning is, if I have a field lines like this and I take a surface, you take a very small elemental surface ds as a vector, g as a vector, take the dot product and integrate it for the given surface. That's what we call as the gravitational flux. At this stage, few things to be kept in mind. When I take this ds, there are certain rules. If it is a flat surface, ds, it is a vector quantity which is having a direction perpendicular to the surface. If I take a spherical surface like this, its small elemental surface can be taken as a flat one. Its direction is always taken as a radially outward direction. See what I'm saying? If I take a small flat surface, the surface element is always perpendicular to the surface in outward direction. If it is a spherical surface like this, or maybe cylindrical surface, it is always taken in a radially outward direction. This is a sign convention for the surface element. This we must keep in mind. Even if it is a cylindrical surface, I told you, and I take a very small elemental surface here, the direction will be radially outward. Radial outward means that if this is the axis, this is the radius vector, it is along the radius in the outward direction. This is for the surface element. So these are some of the basics we must keep in mind, along with the Gauss law. Do you remember? The Gauss law was applicable only when the surface is a closed surface, number one, and is equal to minus g 4 pi summation of mass, and that mass which is enclosed in that closed surface, not the mass which is outside. This gives a great help in solving the problems. Let me take one such problem in detail and give you an idea how this Gauss law helps us in getting the information regarding the gravitational field intensity. In your study material at page number 195, the study material which you have with you, and it's page number 195, a problem is given to calculate the gravitational field due to a uniformly infinite long straight rod. Long straight rod, right? Is the problem given in the middle of it. Let's solve this problem and understand how the flux concept will help us. What is exactly is the problem? We have a very long one-dimensional rod which is uniform. See, in physics, when I say very long, it has a relative sense. If I am interested to find out the gravitational field at a distance small r, rod length, if is very large as compared to small r, I can treat this rod as infinitely long rod. Infinite here in physics doesn't mean that a length which never ends. No, anything where the length is very large as compared to small r, I'll treat that rod as a infinitely long rod. It's uniform. Mass is equally distributed. If I take a section here, and if I take a section here or here or here, I'll find all of these sections of the same length are of the same mass. To handle it, we define a quantity called the linear mass density. Linear mass density. What's the meaning of this? This means that this is mass per unit length. And let's use a symbol lambda for it. Lambda is a symbol here. It's nothing to do with the wavelength and nothing of this type. It is only a symbol. You can choose any other symbol also. And this quantity is constant. Wherever you take, if your length is same, you will find the mass is exactly the same. If I try to solve this problem directly without use of the Gauss law, what I have to do is I can take a small elemental mass, say dm here. I can write the expression for the gravitational field intensity, and that will be always towards the mass. Same I have to do by taking each elemental surface on the whole rod. If I take this elemental mass, the gravitational field will be in this direction, and so on for the whole of the rod. What all we have to do is we have to sum it up. But look, the difficulty level. If I do this, then the gravitational field intensity because of this elemental mass is at an angle, say θ1, but due to this mass, it is at an angle θ2. One thing is sure, that this angle that is changing as I am changing my elemental mass. Not only this, even the distances are changing. Look, this elemental mass is at a larger distance as compared to this elemental mass. So obviously this gravitational field intensity contribution is less as compared to this contribution. So it means distance is changing, angle is changing side by side. So I am getting two variables involved. I can use calculus, but obviously this becomes a bit lengthy process. We have an alternative method and use of what we call as the Gauss law. Let's understand how to use a Gauss law so that we can get the advantage of the Gauss law in solving these type of the problems. Let's revisit this problem again, but this time with a different approach. Now we say that this is the long rod. This is the point of interest where we are looking for the gravitational field intensity. But I will now use the Gauss law. To handle the problem. Gauss law is applicable when you talk about the closed surface. The closed surface are many. You can take a sphere, that also is a closed surface. You can take a cylinder having its top and lid also, bottom also. You can take any other shape, irregular shape also. But preferably what we do is, we take such a closed surface which matches with the symmetry of this system. It is a line, so cylinder is a better symmetrical surface for this. Assume, I'm using a word, assume, it is not really present. You assume that there is a cylinder say of length L, having its axis exactly on this rod. That means the axis of the cylinder and the rod, they are on the same line. Treat this as a closed surface. That means I have the top, bottom and the curved surface around it also. And let's start using the Gauss law. Gauss law says the flux can be calculated by taking the closed integral. This means closed integral. The circle means it is a closed integral. Surface g vector dot ds vector. This is nothing but the gravitational flux. This is a closed surface. Let's divide this closed surface in three parts. S1, the first flat surface on the top. S2, the curved surface around. And the third surface that is at the bottom, g dot ds. Have you noticed? I'm not using now the circle in these integrals, because now if you take individually, these are not the closed surface. If you take only the top surface, it is not a closed surface. If you take even the curved surface cylindrical, it is also not closed. So I'm not using the circles here. Now I use the concept of the surface element. This is the flat surface like this. So if I take a small elemental surface here, it is having a direction like this. Flat surface perpendicularly outward, that is base concept. Due to this mass, the gravitational field intensity is always towards the mass. That is the point. So what's the angle between the two? 90 degree. You are dealing with the dot product. Dot product means G ds cos of 90. Cos 90 is 0. So this whole term will go 0. No need to calculate this. Same happens even for this third surface, S3. It is the bottom surface. Any small elemental here surface has a direction perpendicularly outward, and the gravitational field intensity is towards this rod. Again, the angle is going to be 90 degree. So even this third integration is not going to give you anything. Only one surface is giving you the flux contribution, and that is the surface S2 G ds. Let's see the angle now. If I take small elemental surface here, as I told you, the surface element is always in the radially outward direction. and our gravitational field intensity is towards the mass. So what's the angle between the two? 180 degree. If it is 180 degree, that 180 degree means -1, so I'm using a negative sign out of this integration. So now I don't have any vector involved. I can process my integration easily. I use a symmetry. In the beginning, I told you to take a cylindrical surface because it is a symmetrical surface to the rod. That I did deliberately. If it is a cylinder around this rod, suppose this is a rod, and I take a cylinder around it, then the distance from this rod, anywhere I go on the cylinder, remains the same. If distance is same everywhere, at least the magnitude of the acceleration due to this acceleration due to gravity or gravitational field intensity will remain the same because distances are same. That helps me to take this g out of the integration. And if I do that, minus g, that is for the surface S2. Surface element integrated over this gives you the total surface area. Radius is r, length is l. So this cylinder will have a surface which is equals to 2 pi r into l. So I'm able to get this flux as minus g total surface of this second, that is 2 pi r into l. This is my flux calculation using the definition of the flux only. I'm using many steps in between, but when you are solving it for a problem which is multiple choice, you can skip some of the steps. If you are sure that this is going to be 0, this is going to be 0, you start with the second term only, and you can save a lot of time. Once the flux calculation is done, you can then use the Gauss law in fact. And what Gauss law says? Gauss law says that flux can also be calculated as minus g 4 pi, the total mass inside the Gaussian surface. Total mass inside the Gaussian surface is only this much of the portion of the rod which is having the length L. Rest is outside of it. So I'll not count this mass, I'll not count this mass, I'll count only the mass which is inside. And from my equation, mass is lambda into length. So I will write here, that is lambda into L. I'm taking the length on this side. Lambda into L is going to be the mass. That is the mass inside the Gaussian surface. I take it. This is my equation number 2. I think this point is clear. Let me quickly give you the steps I have done. I use the flux concept to calculate the flux from the definition. Second, I'm using the Gauss law directly, but in that I'm taking only that much of the mass which is inside the Gaussian surface. I'm not taking the mass which is outside. Once the flux calculation are done in these two ways, you equate the two. You can write from equation 1 and equation 2. We have minus g 4 pi lambda L is equals to that what we have done, that is minus g small g 2 pi r into L. You can remove this negative from here, L and L from here. 2 pi also can be removed from this 4 pi, remaining is 2. So your small g will become g, rather 2g lambda divided by r. That is your answer given there in the book. If check it, 2g lambda by r. I'm able to save so much of time in calculating the gravitational field intensity due to the infinite rod. I think the process is clear to you. Let's understand it by taking one more example. This time we are taking a three-dimensional body, a uniform sphere. Now the problem is, there is a uniform sphere of radius r, capital R, and having the total mass capital M. It is filled in this time and uniformly filled. And I'm interested to find out the gravitational field intensity at this point, say G. This point is P, and here, what is the gravitational field intensity I want to know? This distance is R, and this time R is less than capital R. All right. How Gauss law will help me? But Gauss law has one restriction. I can use the Gauss law only when surface is closed. This we have to do from our side. Looking at the symmetry of the system, it is a spherical body, three-dimensional body. So I'll choose a spherical surface having its center exactly at the center of the sphere. And I do that. I say you choose a spherical surface, is a closed spherical surface, is dotted doesn't mean that there is a gap. It is a continuous surface, spherical surface of radius small r, and having a center exactly at the center of the sphere. What I will do now, I'll calculate first of all the flux by definition. Once I get that expression, then I'll use the Gauss law. These two steps I have to do. But since it is a three-dimensional body, I can't do with this linear mass density. I have to use a concept of volume mass density. That is rho. Normally we define the density this way. It is mass per unit volume. I'll use this one this time instead of using the linear mass density because my system is three-dimensional system. First step to calculate flux. Flux by definition is closed integral G vector dot ds vector as by definition. You choose any small elemental surface anywhere on this Gaussian surface. Suppose I choose this one, ds vector radially outward. The mass which is present here definitely will provide the gravitational field intensity towards the center. So the angle 180 degree in this case. So let's use it. G ds cos 180 degree. That makes it integral G ds. Now again I have a symmetry. So in the beginning I am selecting my Gaussian surface, looking at the symmetry, and I'm now using that symmetry. Look, if I take any elemental surface, say instead of at this place, I choose at this place or at this place, the distance is going to be same. So magnitude wise I can say yes, G can be taken as constant everywhere on the surface of it. So you can take this G out. So this integration is now left for surface only. And what is the surface area of a spherical system? 4 pi r square. 4 pi small r square. Do remember this, because I'm taking the surface area of the Gaussian surface, not that of the body. So this is 4 pi small r square. If I have this as the flux calculation from the definition, my next step is to use the Gauss law. And what's the Gauss law? It says that the flux is equals to minus G 4 pi then multiplied by total mass inside the Gaussian surface. That is very important. I should take this mass only. I should not take the entire mass M given. How can I do it? I can make use of this formula now. What is mass? The density into volume. What is density? The total mass divided by the total volume is equals to. Density is the total mass. If I take the entire mass, then I should take the entire volume. But the mass which I am looking for is only in the volume 4 by 3 pi r cube, because I'm looking for the mass which is in the sphere of radius small r. So this helps me to remove these constants, and I can write the mass which I am looking for is m small r cube divided by capital R cube. You put it here, m small r cube divided by capital R cube. All right. So this is going to be my second equation. I hope now you know what to do. We have to equate the two. And if I equate the two, minus g 4 pi r square is equals to minus g 4 pi m small r cube divided by capital R cube. This small r square will remove this r cube and remaining is r only. 4 pi is completely out of the scene. Negative negative also can be removed, and we have g is equals to m capital G small r divided by r cube. So this helps me to calculate the gravitational field intensity in a much easier way than if I use the calculus in solving the problem. So this is the power of the Gauss law, and it's very useful. Look, if you look at this expression carefully, capital R is fixed, capital G is fixed, m mass is fixed, only variable is r. If anybody is moving from this point O in the outward direction, you'll find this r is increasing linearly. So if I make a variation of G, this is capital R, I'll get a straight line like this. And at the center, I have the value 0 because small r is 0. If small r is 0, then entire value of G is 0. Right? This equation already you know. See, we discussed one relation for the variation of G with depth. Do you remember? That was G dash is equals to G 1 minus D by R. It is exactly the same formula. How comes? Assuming that to be uniform sphere, if this is a depth, then the distance from the center will be capital R minus D, which I have taken as small r in my case. If I change this formula as G R LCM R minus D, I can easily write R minus D is nothing but is equals to small r. So G dash will become G small r divided by capital R. And small g is acceleration due to gravity on the surface. I can change this to Gm by r square small r divided by capital R, and you are back to this your formula. So this is what already we have with us, and this is how we have used the Gauss law to get it. So by now I am sure with these two examples you are able to at least understand how one can use the Gauss law in getting the expression for G. Right? Can you go for the next slide? Now we are coming to some of the interesting problem, multiple choice type of problem. Next one. Read this question yourself. And can you give me the answer? Try to get the answer. You have consumed almost 1 minute. Now take a track of the time. We have to build up now the speed in answering these questions. Do it fast. I'm keeping the time. Eight centimeters is the correct answer. Yes, is marked here in the bold, right? 8 centimeters is the correct answer. Very good. Let's see how to handle this problem. Question says that there are two bodies, one is of mass 4 kg and other is of mass 9 kg. They are kept at a distance of 20 centimeter, and I have to locate a point where I'm getting, find the neutral point. Neutral point means that where the gravitational field intensity is 0. On the line joining the two. Of course, I have to take a distance from A. This should also be mentioned in the question. The distance must be taken from A only. How to solve it? When I have a system of two bodies, let's choose such a point P, which I say is a neutral point. It means that at this point, the gravitational field intensity in total is 0. A is contributing to the gravitational field intensity, B also is contributing towards it. Let's take this distance to be x. Obviously, this distance then will become 20 minus x, all in centimeter. Due to A, the gravitational field will be in this direction. It's always towards the mass. Due to B, the gravitational field intensity is towards B. If I can manage to find out this x such that the magnitudes are equal, since they are in opposite direction, the total definitely is going to be 0. Only now the magnitude equality is required. See, I'm using directly the formula. Don't write the details of it. It's not required for multiple choice type of question. It is G, the mass of A is 4 kg. Divide by the distance square, that is equals to x square, must be equal to G9 divided by 20 minus x whole square. Please notice one thing. In fact, if I'm writing everything in SI system, I should have taken 10 to the power minus 4 this side and 10 to the power minus 4 this side also. I'm not doing it. I can skip this because if you are equating the two will be removed easily. So please don't unnecessarily go in the mathematical detailing of it. But you must convince yourself that there is no effect it is going to put to your question, your solution. This G and G is out. A point of precaution. Do not cross multiply and open the square. If you do that, you will end up to a quadratic equation. You can solve it, I'm sure, but that will take more time. The best way is to take the under root at this stage. If you do that, 2 by x is equals to 3 divided by 20 minus x multiplying will give you 42x is equals to 3x, 40 is equals to 5x, and x will be 8 centimeter from A. This also is to be given in the question, so it's missing. 8 centimeter from A. Agreed? Let me give you a shortcut. Sometime we make some cooked formulas available, but with point of precaution. I advise you to do this. For this case, this is A, B. You are looking for the distance from A. You take the under root of the mass of A. What's that? It is 4. So under root is going to be 2. Multiplied by the distance, that is the separation between the two. Then divide by taking the under root of both the masses and add them. That means the 4 kg under root is 2 plus, that is 9 kg is 3, and that will give you 8 centimeter in one step. In fact, what I did, I'm not doing any magic here. I'm using the formula directly. If I'm taking the distance from A, my formula is under root of MA into D, the distance between the two, and under root of M1 plus under root of M2, that is going to be the X. This is the formula. If I can remember this formula, there is no harm in using the formula directly. I can save few steps. If I can save some time, I can make use of this time in doing some other questions. So this directly is a formula which I can use. I have taken this point in between. Can I say that there exists any point on this line outwards this side or this side? Is it possible? If I ask you that is there any point on this side of A or on the other side of the B where I can have the gravitational field intensity 0? Is it possible? No, it is not possible. Why is it not possible? Look at this. If I choose any point here, P, the gravitational field intensity of this at this point is towards A because of A, and because of B, it is also towards B. I may find out a point where the magnitudes are equal, but since directions are not opposite, they can never cancel it out, right? And one of the very interesting thing also to note, that if I keep a body at this point P, at point P, anybody will not experience any force. I can say this body is in equilibrium. Do you know what kind of the equilibrium is this? Is it a stable equilibrium or unstable equilibrium? This is unstable equilibrium. You try to shift this mass slightly towards A or slightly towards B, the body will never return to its position. So this type of equilibriums are always unstable equilibrium, right? So it's the equilibrium position. We call this as a neutral point. There are many ways in which it's asked, but you can't find any point this way or that way. You may find the magnitude matching. Let me do something wrong, which is not possible, just to convince you that the magnitude balancing can be there, but direction balancing is not there. Look, if I take the point on this side, let me call this as X. So how much is this distance? This is 20 plus X. If I start this way, I can write G4 divided by X square is equals to G9 divided by 20 plus X whole square. I can solve this relation 2 by X, 3 by 20 plus X. Crossing it will give me 40 plus 2X, 3X. 40 is equals to X. I'm able to get the answer. But this is not a neutral point. This is not a neutral point. Reason being, directions are not opposite. So they can't cancel it out each other. Magnitude wise, they are same. So this is going to be your wrong answer, right? If it is there. So we have to be careful because we are dealing with a vector quantity. This is very important, right? So going to the next question. This is the answer. Already you know. Next one. Yes. You read the question. I'm taking a record of time. I want the answer to be confirmed in time as less as possible. Answer C, you're saying? Okay, just a minute. We will not declare the answer. Answer is C. That is the correct answer. But let's check it, right? So how the concept we can make use of. Do you remember Kepler's second law? And I told you the areal velocity remains constant, and that is directly related to the angular momentum. So areal velocity is directly proportional to the angular momentum, or you can say vice versa. The geometrical interpretation is that the angular momentum is directly proportional to the areal velocity. So what is the angular momentum? This is what we have to strike. Areal angular momentum is equals to I omega, and I for a point mass is equals to mr square omega. Mass is fixed, so the term which is involved, and he says that there are two variables, one is omega and other is r. So it's one is r, so that's your answer, C in this case. Good. Going to the next question. Skip the solution that is already there. A. Very good. Why is A? Because we did it, right? Sometime if you can remember in your mind and you are sure of it, use it. We say this fair. It's not that we are cheating anybody. If I remember the formula, I can make use of it if it is given there. Look, in the option they have done a very clever thing. It is a maximum to minimum. They are keeping all denominators which are less than the numerator. So they are forcing us to solve. But if I can remember that E comes with a power 1, it's okay. Symbol they can choose any symbol. In this question, they are using the eccentricity with the symbol E. It may be epsilon, it may be anything else, right? Symbol doesn't matter when we handle these types of questions, right? Next one. That is the solution. Yeah. Try this one, keeping a time. One of the very famous question in gravitation. A. A is the correct answer. Very good. Let's understand. There is one of the very important concept in calculus when you are looking for maximum or minimum. And if you know a relation between the dependent variable and the independent variable, the concept is you get the first derivative of the dependent variable, equate this to 0. Let me put it in words, that will be better, right? So whenever a question is on maxima or minima, suppose I have a function, dependent variable is y, it is a function of independent variable say x, and I want to know when this y becomes maximum or minimum. The method is you calculate dy by dx and equate to this to 0. You will get one equation. And when you get this equation, you solve it. You may get many answers for x. If it is a quadratic, you may have value of x with two numerical values. Let me call these values are x1 and x2. I'm taking an example. There may be 3, there may be 4. You take the second derivative of y with respect to x and now put these values one by one. If you get this second derivative less than 0, this is the case of maximum. And if you get the value by putting any one x1 or x2, the value more than 0, this is going to be minimum. This is one of the very important mathematical tool in handling the problem of physics, where you are dealing with such a situation where the maxima or minima is required. As in this case, with this background, let's see how we can handle it. I have a body of mass m. He says that we'll divide it into two parts. One is of mass xm and other is of mass 1 minus xm. If you add, you will get the mass m, right? That's the meaning. And we have to find out the gravitational attraction between these two pieces becomes maximum at a particular distance. If I fix a distance, the force will be F is equals to G xm 1 minus xm divided by r square. R I am not changing. My variable is x in this case. He's asking when will it become maximum, when the gravitational force, and he's asking for the value of x. So I treat my force as variable y and this quantity x as the independent variable x. Now when I'm doing the differentiation, I need not to bother about the constants. G will remain G. I'm not interested. I can go systematically by putting everything in order, but in multiple choice questions we'll do only that much which is required to the minimum. My variable is x, 1 minus x, rest all are constants. I'm taking the separation even constant. Differentiation has to be done for x1 minus x. The quantity is x minus x square. Let's treat this as y. Don't take constants unnecessarily. If I differentiate y with respect to x, this is 1 minus 2x, and you equate this to 0. If I do this, x comes out to be half. But when I say x is half, it can be maximum, it can even be minimum. Although it is required to check it for the maximum. Please do remember, it is not the complete answer. I have to check it. How do I check it? Now I take the second derivative of y with respect to x. The function is this much. 1 will give you 0, and this will give you minus 2. Minus 2x will give you minus 2. And obviously this is minus 2, and minus 2 is negative. I'm in this condition. So if I'm getting this as negative, I'm sure that the condition which I have obtained is the condition of maxima. That's why the answer is A. Is it clear? So in physics, whether it is gravitation or any other chapter in physics, if they are asking for maxima and minima, you can use the calculus. This is the approach which is required, right? Going to the next question. This answer? Yeah. Read the question and try to answer it. This time I'm not giving you the options. is 0? No, it is not 0. It is not 0. Recalculate it. Though its symmetry is there, but the point is not at a symmetrical position. Had this point is taken at the centroid of this triangle, then only the answer can be 0. Symmetry, if is not there, as far as the position part is concerned, it is not there. One and a half minutes are over now. Do fast. Don't take more than 2 minutes to do it. Yes, 2 minutes are over now. We have to be fast. Let me give you some suggestions how to handle these type of the problem. But these cases are the cases of a superposition principle, which means that you are given a system of masses and I'm asking you to find out the gravitational force on a mass due to all the masses given. Rule says that if I have a system of say n masses, m1, m2 up to mn, and I'm looking for the force on a mass say m0, which is a test mass, right? That you can take it like this. You are supposed to calculate the force because of each and every mass. And your final answer should be written like this. The force due to the mass m1 say for example, this is the line, this is the force direction, plus F2 plus so and so on is Fn. You go up to the last mass and add all these forces vectorially. You have to add it vectorially. You can't add directly the magnitudes. You have to care for their directions also. But when such question is given to you, you try to look to what extent you can make use of any symmetry available in the question. See, our question is that we have 3 masses present, each of the value m as given. The separation is small a is an equilateral triangle, but the mass is kept at the midpoint P. The question says there are 3 identical particles, each of mass m, placed at the corner of an equilateral triangle of side A. Find the force exerted by the system. Check this point, not by any individual particle, by the system on another particle of mass m placed at the midpoint of a side, as shown, right? In this case, see, if I put any mass here, let me put this mass as m0. These are the m masses. How should I proceed? I should think first of all that this mass will experience the gravitational force because of all the 3. But look at these 2 masses first of all. If this mass is trying to attract this m0 on this side, this mass will try to attract it on this side. Since it is kept at the midpoint, obviously these forces are not going to add at all. Don't calculate them. You try to avoid unnecessary calculation if you use, say, some of the concepts to minimize your efforts. See, you can do the question in less time only when you can avoid some of the unnecessary steps. No need to calculate. I am not interested in this. This mass definitely will put a force. This is only left mass. But the thing is that they haven't given us this distance directly, no problem. At midpoint, if you draw a line, it is going to be perpendicular. This side is a, this side is a by 2. So this side is going to be a square minus a square by 4. Under root lena, don't take it, because later on I have to take under root square of it. Once you take under root and then you take a square, this doesn't matter. This is going to be 3a square by 4 as a distance square. Let me put this as r square. So my answer now will be g m divided by 3a square by 4. Now when they give this type of the question, sometimes they even ask for the direction. So for the direction, if they have marked it as A, B, C, so you can say this force will be towards A. Though it's not specifically asked in this question, but sometimes they give the formula or the expression along with the direction part. So please do care for the direction also. So sometimes they mingle up the things. They give the same magnitude, but with the wrong direction, right? To be safer on this side. Yes, next sir. Now question on percentage. One minute is over. I'm putting a pressure on you. You have to learn to handle this pressure. Do the things faster. And at the same time, you have to do it accurately. Fifteen more seconds to do. Time is over. We have to learn how to do it fast. Are you able to recognize that which formula is applicable in this case? Variation of g with angular velocity of revolution of Earth about its own axis. That is the first step which you have to do. And the formula is g dash is equals to g minus r omega square cos square lambda. Do you remember this? The formula? Now, when they give the percentage, you have to look carefully to understand how the percentage is given to you. See cleverly what they have written. They are saying that the weight of the body, it appears 40% less in its weight at equator. What's the weight at equator? The weight at equator is equals to g minus r omega square. Why so? Why so? Because lambda at equator is 0. When I say 40% less, it means how much now I have the weight? 60% only. They say that this must be the 60% of the weight, less weight at equator. What would be the angular speed of Earth so that the body lying on the equator may appear 40% less than its weight at the equator? Do you think when the body is lying at the equator, its weight can ever become 40% less than the weight? But that means the weight, the normal speed of the angular velocity. So when I say this, I mean that this omega is the natural angular frequency of the rotation of Earth. But when I say the 60% of it, that means 60 out of 100, that is with a new value of angular velocity, and that is mg minus r omega dash square. I'm saying this omega. See, look at the question carefully again. What would be the angular velocity? What would be the angular speed or velocity of the Earth so that the body lying on equator may appear 40% less in its weight at equator? At present, if anybody is present at the equator, its weight is determined by the effective acceleration due to gravity g minus r omega square. If there is a change in the value of omega dash, then the effective omega becomes g minus r omega dash square. But what all we have to do is this. See, if I take this is 3 by 5. If you divide it by 20, cross multiply it, take this 5 on this side. This is 3g minus 3r omega square, and this is equals to 5g minus 5r omega dash square. I take it on this side. This is 5r omega dash square is equals to, bringing it on this side, it is 2g. Omega dash obviously will be equal to how much? 2g divided by 5 of r under root. Check it again. This is the g now present at the equator. In a new situation, when there is a change in omega, this is omega dash, this is going to be the effective acceleration due to gravity. 60% of this, I am not taking 40%. See, the clever thing, what they have done, 40% less. Please don't use 40% here, because what now is present is only 60%. So with percentage, this is always, this is a point, you must not forget this point. Then we are equating it. And then rest is the mathematics. Once you get this value, all things are given to you. You can calculate it numerically even if it is required, or if the options are given in this format, that's very nice. Right? This is 3 by 5 multiplied by 5 this side. Take it on this side, this becomes positive. 3g on this side will become 2g. And when it's 2g, divide by 5 of r. G also is given and r also is given to you. Right? Rest is numerical value, how to handle it. But this is what the expression we get to solve. But here I would like to give you one important concept. I think this point is clear to everybody, right? No? Huh. Minus 3r omega square. Yeah, this also is to be taken care of. Right? That's, I forget to mention it. Yeah, this is there. If you take it on this side, this is 3r omega square will also be there, and that is equals to 2g minus 3r omega square divided by 5 of r. Yeah, that is to be there, right? But anyway, let me tell you very honestly, this value is very, very small. You know why it's small? What is omega? Omega is 2 pi divided by the time of revolution, and time of revolution is how much? 24.3600. And look at this, you have even omega square involved in this. So this value is obviously going to be very small. But anyway, this is more accurate value for omega dash. That's true. With percentage, there are few more things involved. Let's take one example. And when the percentage changes are concerned, see, small g is given by the formula gm by r square. R the distance, right? Distance from the center of the point of concern, right? M is the mass. Mass of the planet is fixed and r is the distance taken from the center. If I say that the radius, or you can say the distance from the center, is increased by say 0.1%, it is increased by 0.1%. Can you tell me how much change in the value of the g will be there if the distance is increased? If I increase the distance by 0.1%, can you tell me how much is the change in the value of the g in percentage? Again, it decreases by 1%, 0.1%. One more try. 0.01%. Any other answer? See, now I'm giving you one suggestion to handle these type of the problems. Look, when changes are small, I'm doing it with one case, when the changes are small. Actually, small has no sense in its own. I can treat this 0.1% to be large, that depends on me, or I can treat this to be very small. But if it is in fraction, or even if it is 1% or 2%, you can use this method. We use the error formula to handle this type of the problem. Before you use it, you recognize, first of all, what are your constants. In this formula, capital G is constant, mass is constant, I'm not changing the mass, planet is same, capital G is a universal constant, the only variable is small r. I advise you to do like this. You take the log both side. Log natural, normally we take in physics log natural. This is equals to log of gm minus 2 log of r. Am I right? Because when you take a log, this power, because it is in the denominator, this will come in a multiple as minus 2. Differentiate this. This will give you dg by g, but the differential of a constant is always 0. So you are left with minus 2 dr by r. Multiply by 100 both sides, so that you can talk in terms of a percentage. What I did, I changed the percentage of r by 1%, and that is the increased value. If it is plus 1, the positive 0.1, so the answer will be minus 2 multiplied by 0.1. Minus 2 means that there is a decrease. This formula will give you automatically this thing also, and your answer is 0.2%. Is this clear to you? On this line, for the same question, if I say, this is a case 2 now I'm taking, if I say I increased the distance by 100%, if I increase the distance by 100%, please do not use this formula. Why so? Because when I take this dr stands for small change as compared to r. This formula then will be is not applicable. This is the error formula, and this error formula is applicable only for the case when the changes are very, very small. Then what we should do? The first thing is that I should not use the error formula. How to proceed then? Then you can proceed directly. Look at this. G m r square is a first case. If distance is increased by 100%, now what is your new distance? R, 100% increase means it becomes double. Now the distance becomes 2r. So new value of the G dash will become Gm divided by 4R square. 2R whole square. That makes it 4R square. It means this is a new value which becomes 1/4. If something from 100% goes to 25%, how much will be the change? 75%. So there will be a decrease in value of the G by 75%. I can't use this formula. If I use this formula, I could have answered it at that there is a decrease by 200%. Is it possible? The G decreasing by 200%. This is something which is not possible. So remember, whenever there is a question on percentage in physics, first thing you should put to your mind, is it the percentage change? As I given in this case, it is 40% less. That means the remaining is 60%. Sometimes they say that the value is decreased to 40%. If they say value is decreased to 40%, then even finally it is 40%. So there is small things which you have to keep in mind. And if the changes are very small, then use error formula. If changes are large, then please do not use the error formula, do it directly. You can solve even this problem directly, but your answer will come out to be 0.200 something 4%, but that is very close to 0.2%. And in your options, if the answers are given close to it, you can tick that out. So I hope this point is clear to you. It's quite crucial point as far as the percentage part is concerned. Next. Yes. This is a bit lengthy, but let's try this. Try this. The mathematical tools are with you now. Trust yourself. Apply the mathematical tools you have. Start doing it now. Yes. Direct proof. Answer. Answer is B. But how directly we can say this? We have to. You have done it? Okay. So you remember the answer, right? But let's see the details of it, right? Before we go for then to the next question, let's answer this, right? But what he says that there is a ring, and this is the axis of the ring, and one moves on this axis from one point to another, and this is the origin. As we are approaching this ring, what we notice is that gravitational field intensity is increasing. But as we are coming very close, we find at one stage it starts decreasing. It is showing this type of the variation. Why it is showing this type of the variation? Because of the function involved in it. If this is of mass m and is of radius r, coming at this center, it is a symmetrical position. Any point mass kept at this point O will experience equal force from all the sides. So definitely there is no net force. So we can say that the gravitational field intensity becomes 0. Even at infinity it is 0. But when we are approaching it, now these masses, they try to attract it. So obviously it is 0 here and 0 here. It must have to pass through a maximum only. Then only you get 0, maximum, and again 0. But my interest in this question is to apply the calculus to handle it. If I have this ring and I'm asking you to calculate the field at one particular point P, say at some distance r, this is capital R, how can I do it? Once again, I have to use the concept of, say, dividing the system into small parts, writing down its contribution and integrating it. But in this problem, I am teaching you one more thing, that you do it in pairs. And what's that? Look, if I take a small mass here, say a value dm, and I ask you to write the expression for g, or rather in this they have used the symbol E, so let's use the symbol E, dE. Can I say this dE is equals to g dm divided by r square plus small r square to the power half, and then you have to do the square of it, that is one and the same thing. Can I say this? Obviously at certain angle. But this is a two-dimensional case. If I take this direction, I have to cover up a cone type of arrangement in order to take all the contributions. I can save a lot of time if I select an elementary mass at a diametrically opposite end. How can I save this? Let's learn this. If I take this mass exactly of the same value here, it is a symmetrical system. I have now the contribution in magnitude exactly the same, but in this direction. Gravitational field intensity is always towards the mass, always towards the mass. This angle is going to be the same as this angle because of the symmetry. If you look at the cone structure, right, as a cone, this angle with the center makes the same angle as the diametrically opposite end is making. Since this gravitational field intensity is a vector quantity, you resolve it. You break it up into two components. One in this direction, that is equals to dE sine of theta, and one along the axis, that is equals to dE cos of theta. Agreed? Do the same for this contribution also. It also has one contribution in the vertical direction like this. Again dE sine of theta, and the component in this direction, that is dE cos of theta. Why we are doing it? Look at these two. dE sine theta in this direction and dE sine theta in this direction. What do you expect will happen? They will cancel out. Not only for this pair, any other pair if you take, if I take the pair like this, say at this end and at this end, we have the same, the vertical component is always going to be 0. The only surviving component will be along the axis. So we make one statement that the effective value of the gravitational field intensity is g dm r square plus small r square cos of theta. I'm not taking the sine component because sine components are not contributing at all. So the effective value will be cos of theta. This is the power of by taking it in pair if the symmetry is there. So now or rather I will write this as effective because d is this much. So this cos theta will be the effective value of the d, which is counting. The rest part is not counting, so forget about that part. Let's change this cos theta. G dm r square plus small r square. And what's the cos theta? Cos theta will be the base to hypotenuse. Base is small r square plus small r square to the power half. Am I right for this? So now I have d effective is equals to G dm r divided by r square plus small r square to the power 3/2. Can you recognize the variables in this? Because before integration, this is a point of precaution. Everybody must take this precaution that we must recognize the variables and then we proceed to the calculation, right? G is a universal constant. dm means is a variable, right? Small elemental mass you have taken, that's a variable. What about small r? At a particular point, this is fixed. Capital R is fixed, small r is fixed, so rest all are constants. So only variable is dm. If I ask you what is the effective value of the gravitational field intensity, you can take all constants out. G r square plus small r to the power 3/2. Integration will be only for dm, and that will be nothing but the mass of this ring. And the mass of the ring, let's say this mass is equals to capital M. They have given a capital M, so I'll put this as capital M. This is the first step. Of course, if you remember it, it is very nice. Otherwise, also you can obtain it using the symmetry in pair formation, right? But this is not the exact question asked in this case. They're asking that where is going to be maximum, and I told you for maximum we have one good technique with us. Do the differentiation, equate that to 0. Do the second differentiation. If you get the value at negative, we say this is maximum. Sometime it is done even if you do the first derivative and use a bit of intelligence that how we can get it. Look, this is the maximum, this is the minimum. So minimum is not asked. So at any finite distance, whatever is the extremum we are getting, that is going to be the maximum. So we do only one derivative. We will not go for the second derivative. Look, now we are heading towards the main part of the question. And the question is, you have to get the condition for the maximum. What I'm doing is, look at this, the way I'm doing. This is not an exact way of doing the things, but while doing this derivation, I treated r to be constant. But if I am moving from one point to another on the axis, I'll treat this small r as variable. So look, I was calculating the gravitational field intensity at a point. I have to fix a point. If I am fixing a point, my r, small r is fixed. But when I am moving on the axis from one point to another side, obviously the small r is changing. If small r is changing, so this time my small r is variable. So from this relation, gm by r square plus small r square to the power 3/2 and small r, this function is my variable function. And the variable physical quantity is small r in this case. Don't care for the gm. It's not required. Because that constant will remain constant, it's not changing, so there is no need to write this. But small r is there in the numerator, small r is also there in the denominator. So for differentiation, I have to use a quotient formula. And what's that? You take the square of whatever is there in the denominator. I hope you remember the formula u by v, v square, this is what I have written. derivative of the numerator with respect to itself. R derivative with respect to R will give you 1. Don't write it. Multiplied by whatever is there in the denominator. Plus or minus? Minus. This time R is to be kept as it is. We have to do the differentiation of what is there in the denominator. 3 by 2 R square plus small r square to the power 1 reduced, that is equals to half, but that is not sufficient. We have to differentiate whatever is there in the bracket and we have to multiply it. R square this time is constant, radius of the ring is fixed, but smaller is variable. So variable is only R square. So its derivative is going to be 2R. And this whole is to be equated to 0. For extremum, this will come on this side, 0. So that means I have to equate the 2. If I do this, R square plus small r square to the power 3 by 2 is equals to R square. Because of this, 2 part will be out from the scene. And this will now becomes R square plus small r square to the power half. You can remove this and this will be now 1. That means I have R square plus small r square is equals to 3 R square. R square is equals to 2R square. So R comes out to be plus minus R by root 2. That is your answer, which is B. Okay. So by this question, I actually plan to teach you how to use calculus in order, first of all, to calculate the gravitational field intensity and then to make use of it to find out the maxima and minima condition. These two are the crucial steps, mathematical tools you can use in physics, whether it is a case of a gravitation or even in case of electrostatics. You have the similar type of the question. Only thing is that they'll say that there's a ring and there's a charge on the ring. You have the similar type of things there also. So as I told you in the beginning, that this chapter is quite important because similar chapter is there in your 12th class. So some of the concepts are common and we can make use of it. I hope this point is clear to you. So by now you must understand how to use calculus for getting the result from a continuous body and for getting the maxima and minima. Next question. This is all. Yeah. A use of calculus. Would you like to do this yourself? Try it once. Try it once. This time it is a semicircular ring of mass m and radius r. It is not a complete ring. I am giving you a continuous body, asking for the calculation. You have tools with you, calculus, apply it. Yeah, sure. Then I'll stop at that time. Let me help you a bit. This is a semicircular ring. It says the mass is m, radius is r, and we are interested to find out the gravitational field intensity E. This E is at the center. Gravitational field intensity at center due to semicircular ring of mass m and radius r is E. And the concept is that you have to take a small elements, write the contributions, and then you have to sum it up, right? That's all you have to do. So whatever I taught you in the previous question, you have some of the application in this case also. Let me help you a bit. Take a small element here, dm, and saying that this small element is a part of a small arc which is confined by an angle theta, and this thickness is d theta. Use this concept. It's basically semicircular, so you can define a quantity mass per unit length, and length is nothing but is equals to pi r. This 2 pi r is the complete length. It's semicircular, the length is pi r. So this is the linear mass density. Mass density. This will help you to write the mass of this small element. If its angular width is d theta, can you tell me how much will be its length? Concept of angle. Angle is arc by radius. So d theta is equals to arc by radius. So arc length will be equal to r d theta, right? And if you have to write the mass you can write lambda r d theta. So this is how we can write the mass of this element. And what about the gravitational field intensity direction wise? This will be definitely towards it. Let me make one diagram of the similar type where I'm showing only the gravitational field intensity dE. This is towards the mass starting from the point O of concern, which makes an angle d theta. What's the magnitude of this dE? Magnitude, I'm not talking about the direction part. Direction already I have plotted. This is equals to g, the mass, lambda r d theta, divide by distance square. So what is the distance? Nothing but the radius is r square, not small r square. Or small, I've taken a small r, let's put this as capital R, so that you do not get confused with this. I have did in the wrong way. R. So this gives me g lambda d theta divided by r. Okay. Can I do the integration at this stage? This is a crucial point. Can I do the integration at this stage? Yes or no? No. Why not? Integration means summation, and when you are dealing with the vector, unless they are in the same direction, you can't do the integration. This is what we discussed in the previous case. I did it in pairing formation. Let's do one thing. Take a component of it on this side. How much is this? D cos of theta. And what is its component here? dE sine of theta. You agree with this? Toward the side of theta, this is dE cos theta, and to other side it is equals to dE sine of theta. Do one thing. Take a similar elemental mass here at the same angle theta, same mass dm, same angular width, but angle is taken now from this side. Magnitude is dE. If I resolve it once again, dE cos theta on this side, and on this side this is equals to dE sine of theta. What I notice once again, dE cos theta, they are equal and opposite, they will go out of the scene. What is left out? dE sine theta. And they all contributions are in the same direction, so I can go for the integration. Integration of a vector cannot be done unless until you find the quantities are in the same direction. So this is not the dE to be taken, to be integrated. I have to go for the dE effective, where I have to put a sine theta there. All right. Now I can integrate this to find out the total effective value. And what's the total effective value? G lambda out, constant. Capital R also is out. And what we have now? Sine theta, d theta. Can you tell me the limits now I have to put? I want to cover the entire half ring. That is from 0 to the value pi. Please don't use 180. It's not recognized in the SI system. It is a radian which is the unit. So I have to write this from 0 to pi. Sine theta. What is the integral of sine theta? Minus cos theta. Differentiation of sine theta is cos theta. But when you go for the integration, this becomes minus cos theta. It's all right. So let's put the value. So E effective will be now G lambda by R. We'll put the value of lambda in a minute. So what is cos pi? This I write as minus cos of pi minus cos of 0. I can choose the negative to be outside, but anyway, no problem. G lambda by R. What is cos pi? Cos pi is minus 1. Minus of this will make it 1. This minus and minus will be plus, and cos 0 is 1. So what I am getting? 2G by R. Now is the time to put value of lambda. Lambda is m pi r. So this becomes 2gm pi r square. So your answer is C in this case. Somebody answered this. So Sudha Madhvishi has answered this one. That's the correct one. Answer C. Good. Processes to be learned. That is important. See, the pairing is helping us to remove some of the components which are unnecessary. So by now, I'm very sure you must have learned how to use calculus. I can't simply do that. I divide the system, I write an equation, and I go for the integration. Don't do it blindly. When you are dealing with the vectors, you have to care for it. Okay, let me extend this question. Is it clear to everybody? No confusion? Let me extend this question. We are talking about the gravitational field intensity. What about the potential? If I say, okay, this is the semicircular ring of mass m and radius r. Can you tell me the gravitational potential which I used to present by V? Gravitational potential at the point O. What is the gravitational potential at point O? I'm changing the nature of the quantity. From gravitational field intensity, we are coming to the potential. Is potential a vector quantity or scalar quantity? Scalar quantity. and the value for a point mass is minus gm by r. This is the formula for a point mass, but it's not a point mass. If I take a small element dm here, I can write my contribution as minus, I should not miss, this is important, g dm by r. Do I need to change dm? In this case, no, because already this is scalar. We did it in this case. We did it in this case because we were dealing with the vector quantity. So I have to make somehow the component direction to be same. But for potential, I need not to bother. I can go for integration directly, and I write the potential is equals to minus g m divided by r directly. No need to have the component in pairing. So please remember, for vector you have to be extra conscious. But when you're dealing with a scalar quantity, and if you are sure your variables are only dm in this case, rest are constants, you can go directly. You should not be over conscious, right? For scalar quantities, you have a bit of freedom. That is the power of this scalar quantity potential. Once you get the field intensity here, they may ask not only to calculate the field intensity, they may ask for a force. Suppose I put a mass here, and they ask you to calculate the force. No problem. Once the field is known to you, since it's a unitary method, if I place here a mass small m, the field multiplied by small m will be the force in the direction y. This potential is calculated. You can even work out what is the potential energy. And for potential energy, you have to multiply it with the mass again. What is the mass you are putting at the point O? This is how we manage to go for the scalar quantities. I think it's clear? Yes. Yes. One of the very much applied part from the concept of the potential energy. There are two spherical bodies of mass 2m and m. Their radii are 3r and r respectively. They are held at a distance of 16r. The center to center distance is 16r from each other in free space. Free space means that there is no friction. When they are released, they start approaching each other due to the gravitational force of attraction. And the question is, then find out their velocities at the time of impact when they collide with each other. What will be the velocities? But when you have these type of the question, the very first thing you try to think is that what is the concept one has to apply. Although he is making it very clear that this is the case of a gravitational force. So one thing is clear, that you have to handle it by using the gravitational force concept. Now there are two approaches. There are two approaches, as I told you. One, you use the concept Newton's law of gravitation, and other is a case of potential energy. In my last lecture, I put this point that in mechanics, we always solve a problem. There are two options for us. Maybe that one option may not be applicable, that is a different matter, but there are two options, using a force concept and using the energy concept. Which we should choose? This is the crucial point, because this is your starting point. If I start it with the force concept, because they are talking about a velocity, my approach will be, I'll calculate first of all the force. From the force, I'll come to the acceleration, and from the acceleration, by integration, I'll get the information for velocity. This is the route. But there is one problem. As they are approaching each other, their separation is reducing. If separation is reducing, the gravitational force of attraction continuously keeps on increasing. It means the force of gravitation is not constant in this case, it is variable. If it is variable, the acceleration will also be variable. So we have to get the expression for the acceleration, then we have to find out the limits, and we have to integrate. This is one plan. And what's the plan B? Potential energy. What's the advantage? It's a scalar quantity. You need not to bother about the direction. Of course, that also is changing. But I have one relief in this case. Do you remember the first slide on the Newton's law? I've written some important properties of the force, and I told you that this force is a conservative force. When I say it's a conservative force, what does it mean? The work done does not depend upon the path followed. It depends only on the initial and final position. In between, what is the situation? I need not to bother. So this second plan is more comfortable for us. So I advise you to choose the second plan rather than doing it with the first plan. That can also be done with the first plan. Calculus is such a powerful tool. We can make use of this to get it, but I advise you to in a better way to use the second plan, that is the energy plan in this case. And look, we are interested in velocities. So potential energy from the energy conservation can be related to the kinetic energy they are going to get. And from there I am able to make out. So let's work with the second plan. So when you have such type of the question which are more involved questions, you give thought before you start it that how one should approach it, and try to select the right and the comfortable plan rather than starting it with the calculus. Though calculus can also solve it, but why should we waste time on this? Let's how to handle it. I have a situation where I have two bodies. This radius is 3r, this is r, mass is m, and its mass is 2m. So definitely there is a potential energy of the system. Let's write the expression for the potential energy. Can I write this as G 2m into m divided by 16r? Don't take the square of it, because for potential energy is only the distance with the power 1. Agree with this? What happens when they come close to each other? At the time of impact, suppose this body is moving in this direction and this body is moving in this direction. Say this is having a velocity v1 and this is having a velocity v2. They can't go beyond this. They can't. We are saying that there's an impact at the time of impact. What happens later on, we are not interested in. So what now is a separation? R and 3r, that means equals to 4r. What will be the potential energy in this situation? Minus G 2m m divided by 4r. Which is more, U or U dash? U. This negative sign is very, very crucial. In the previous lecture, we also have realized it. So it means that my system is going from U is more than U dash, means my system is going from high potential energy to low potential energy. If it is going to the low potential energy, where the additional energy is going? Where the additional energy is going? That is going in the form of kinetic energy. I can write one thing, half 2m v1 square plus half m v2 square is equals to, this is higher, U is higher, minus G m square. I'm simplifying it a bit. This is 8r, and minus, that becomes plus G m square by 2 of r. Is it okay? You please keep a check, right? Is it clear? But I'm now stuck in a one situation. I have unknown quantities v1 and v2. There are two quantities and I have only one equation. Is it possible for me to handle this way? At least I need one more equation. Can you suggest one equation which I should add in order to solve it? I gave a hint in my previous lecture. Momentum conservation, but that is a conditional one. Very good. Momentum conservation. Can I use the momentum conservation? First of all, this is the point. Yes, if I choose this as my system, because the force of attraction from the two, that is obviously the action and reaction pair, equal and opposite. If it is equal and opposite, what is the total of it? Total of it will be 0. It means net force on my system is 0. And conservation of linear momentum can be used. Initially, they were at rest. There was no linear momentum in the beginning. But at the time of collision, I write this as 2m v1 minus m v2. Is it correct? I'm using a negative sign. Why I'm using a negative sign? Because we are dealing with vectors. For scalar, no issue in that. This negative is a different reason, right? But for kinetic energy, I have just simply this is always positive. So here I have to be careful because this with V2, it is going in the opposite direction. And we are dealing with a vector quantity. So minus is to be taken care of. So from here, I have twice of V1 is equals to V2. Now, the situation is quite easy for me to handle. How comes? Look, if we can simplify a bit, let's simplify. M can be removed. Right? This 2 also can be removed. So is V1 square. V1 square plus V2 square. And what is V2? Twice V1 square. Square of that will give you 4V1 square. Divide by 2 will give you 2V1 square is equals to 1 by 2 minus 1 by 8. 1 by 2 minus 1 by 8. 8 being LCM will give you 4 minus 1, that is 3 by 8. GM by R. 1 I have removed, right, from the C. So this gives nothing but is 3V1 square is equals to 3GM by R. 3 can also be removed. V1 is equals to under root of GM by R. GM by 8R. Sorry, 8 I have missed. 8R. Once V1 is known to me, I can write V2. This equals to twice of this. If I take the 2 inside, this will become under root of V2 will be GM by 2R. So this approach is quite comfortable approach because it depends only on the initial conditions and the final condition. Do not unnecessarily go for the force concept, right? Variable quantities, and if there is no other option but to go, then one has to do it. That's a different story, right? But this is another approach. Do we have time to go for the next question? Okay, I'll go to the next question quickly. Question is, there is a particle of mass 1 kg placed at a distance of 4 meter from the center on the axis of a uniform ring. Ring has a mass 5 kg and its diameter is 3 meter. Find out the work required to increase the distance of the particle from 4 meter to 9 meter to 5 meter. This is 5 meter, please. Take it as a 5 meter. From 4 meter to 5 meter. Take this as a 5 meter, right? I have missed it somehow. Tell me the approach to be taken. What is required? Work. You can calculate work again by 2 methods. One, force multiplied by distance, taking the angle also preferably by cos theta, and then going for integration for whole of the system. Why I'm insisting on integration? Because force is not a constant, force is variable. Is there any other approach? Yes, there is another approach, and that is the approach of energy, potential energy. So for that, you should know That's if I have work done by some external agency, then you should take the final potential energy minus the initial potential energy. But if it's work done by the gravitational field, then it should be taken as initial potential energy minus final potential energy. Because of the sign convention, we have this type of a situation. So we prefer to do it by this method. But how to write the potential energy expression for any distance? I have with me now a one simple situation. If this distance is r, we just have discussed that the potential at this point will be written as minus gm by this distance. This is capital R, this is small r. So obviously this is equals to r square plus small r square under root. Am I right for this? Right? For vector, I have to handle the direction. But for scalar, this is capital R, this is small r. So obviously this distance is equals to r square plus small r under root. For each and every point on this ring, the same is the distance. So I can write at this particular point the potential as minus gm by r square plus small r square. So once the potential is known to me, what I can do, I can multiply by the mass which I am putting at this point to find out the potential energy. So for the potential energy, I have the formula gm m divided by under root of r square plus small r square. Rest is mathematics. I have to take now two distances. One is 4 meter and another is 5 meter. This is nothing but is small r. That is the distance from the center to be taken. Capital R is now given to you. You can easily put the values, find out the difference, and you can calculate the work. Right? So this concept of the gravitational potential energy for finding out the velocity, for finding out the work, it is quite useful. And we are exploiting the conservative nature of the gravitational force, because path is not important now. Right? Even if we are going by curved path, the work done is going to be same. So now let's come to the online questions. First one. How do we calculate the percentage in change G with percentage change in R and M on the planet? Right. See, small g is equals to capital G M by R square. If the changes are large, then we have to do it directly. If the changes are small, then we can make use of the error formula. Let's take it with the help of an example, and that is I have a planet of mass m and its radius is r, and this is the value we are taking on the surface of it. There are two possibilities. They may say, yes, the size of the planet is changed. Let me do it with an example, that is 2r is made, and the density is kept constant. Please notice this particular condition, if it's there. And sometimes they say that there is a similar planet of similar density, but the size is double. Then in this case, the new value should be taken in this fashion. Mass definitely will change. If there is a radius change to double, its volume will become 8 times, because volume is 4 by 3 pi r cube. So if radius is twice, then cube of it will make it 8 times of r cube. So mass becomes 8 times. You please care for this. and the distance from the center also increases to 2r. So this becomes 4r square, and that gives you 2 gm by r square, and will become twice of g. All right. And if they say that there is a planet whose mass remains constant, but the size becomes 2r, no need to take this volume contribution. Then we can simply say, yes, the g is inversely proportional to r square, because now my mass is constant. So just increasing it to 2r will make the g dash to go g by 4. So whenever there is a change in the, say, radius or the mass, you please notice that what remains constant, and accordingly you go for it, right? So in this particular case it is twice, in this case it becomes g by 4. Can you just go to the question number 6? What was the question number 6? I don't remember exactly. What would be the angular velocity of the earth when the body is at equator? See, I quickly revise this again. So what they say, there are two situations given. One is a normal case when earth is revolving around about its own axis and one person is at the equator. The effective value of g here is equals to g minus r omega square cos square lambda will give you 1, because lambda is 0 for the equator. So this is the normal value of the g at equator. But if now earth starts revolving with some new value of omega dash, suppose there is some kind of a collision from external body and there is a change in value of omega. So in that situation, g dash, as he is demanding, should be 40% less. When it is 40% less, means that becomes 60% of its value. That means 60% of the value g minus r omega square. And he's asking now, what is this value? If I do that, I'll use again the similar relation for it. I should write this as r minus r omega dash square. And if I divide by 20, this gives you 3 and this gives you 5. So this becomes 3 by 5 times of g minus 3 by 5 times of r omega square. I'm interested in this r omega dash square. You take it on this side. If you bring it on this side, this will become 2 by 5 of g. This is 2 by 5. If I take it on this side, this becomes 2 by 5 of g, and there's a value of minus r. And then, sorry, this is now 3 plus 5 r omega square. Yes, we have done in that wrong way, minor calculation. Anyway, so that you can write this as omega dash square is equals to 2 by 5 g plus 3 by 5 of r omega square, divide by capital R, and if you do the under root of it, you'll get the new value of omega dash. So this should be the correct answer. I did it the wrong way, and then taking the other term on that side. But this relation we have written, and you can solve this relation according to the requirement whatever is given. Then coming to the next, page number 198. Page number 198. Question number 7. Question number 7. It says the uniform ring of mass m are placed directly above the uniform sphere. So question says that a uniform ring of mass m and radius r is placed directly above mass m, and radius r is kept directly above the uniform sphere of mass m and equal radius. And at a separation which is equals to root 3r from the center of the sphere. A figure is not given, so this is a figure for it. The gravitational force exerted by the sphere on the ring will be. What is the force between the two? See, he's asking, what is the force which the ring experiences because of the force? It is exactly the same the sphere experiences because of the ring. For sphere, if the point is lying outside, you can treat this as a point mass. But for the point which is lying outside, not for the point lying inside. Inside there is a variation of g, but for outside point you can do that. So I am making a small simplification of this problem, and that is I am treating this sphere as a point mass. I can do that for the outside point, and now I have a ring. This distance is root 3r, and this distance is r. This is the same situation which we have worked out the gravitational field intensity of a ring at a particular distance. Or you can do it directly also. There is no need to remember the formula. You can do it directly. How you can do it? Look at this. If I try to find out the force experienced by this mass due to this element, this will be nothing but is root 3r, this is r, this comes out to be 2r. So the force will be, let's go straight away to the force. Let's not go to the field and then to force. You can do it directly. This will be dF is equals to g dm, the mass of this element. Mass of this body is capital M, and distance will be equals to 2r whole square. That makes it 4r square. But the thing is, this is a vector quantity. I take another element on this side. If I do that, then which vector will survive? I hope you now know. If this is df, this is df, this angle is theta, the only surviving component will be cos of theta. So I do one thing, I put effective here and put cos of theta. And what is cos theta? Cos theta is equals to the base by hypotenuse. And go for the integration. If you go for the integration, this will be the mass m, right? And you simplify, and that will be the total force on it because you have done the integration. Because now you know the technique. Don't write all the steps. Go directly, solve it, and you'll find your answer. I hope this is clear to you. You can use the direct formula for the gravitational field intensity and put the mass there to get the force, or you can drive. I gave you the technique to do it. Next question. That's it. Any more questions from your side? Yes. Is it from the book? Yes. Page number 197, example 4. Example 4. Gravitational field intensity at the center of an arc given by the arrangement. If it is not a complete circle, the integration will not be from 0 to pi. We did this case. Will be from the given condition for that, right? So integration, look at this. The integration he is doing from 0 to alpha by 2. Alpha is that angle which he has taken. Look what he has done. He has taken an arc and he says that this angle is alpha. So this is taken from 0 to alpha by 2 for this part. Whatever the contribution this is giving, the same is the contribution given by this, you multiply by 2. You have a factor of 2 multiplied there. If you look at the equation, it is written as 2 dE cos theta in the third line. E0 is equals to twice. What he is doing? He is taking the contribution of this half and this half and summing it up from a range from 0 to alpha by 2. Technique is once again the same. Why only the cos component? Why? Because sin component cancels out, right? So this is how such type of the cases where the distribution of mass is given in any of the fashion, you can make use of it. Any more doubt? Is it clear? Can we stop now? Or if you have any query, or let me ask one question from you, right? I have enough time to ask one question. Normally the trend is that they may not ask you the question directly from gravitation only. They may mix something. Suppose there is a ship and the ship is moving on the equator from west to east. Say initially it was at rest, having a pendulum. Diagram is not to the scale, just to understand this. Initially it was at rest, and this pendulum is oscillating with the time period, say t0. Pendulum is oscillating. Remember, time period of the pendulum is 2 pi under root of L by G. Now this ship starts sailing from west to east with a uniform velocity v. This is constant. And now the same pendulum is oscillating and its time period is t. Can you tell me, is t less than t0, t greater than t0, or t equals to t0? The mixing. Simple harmonic motion is now mixed with the gravitation through G. Through G. The ship was on equator. Ship moves on the equator with constant velocity v. What happens to G and then to the time? Formula is with you. Formula is G dash is equals to G minus R omega square, for equator at least. Cos square term is not there. What happens then? Find out the quantity which will change when the ship is in motion. Radius of the earth is constant. Omega. Is it increasing or decreasing due to the motion of the ship? Decreases or increases? See, try to understand. You have to make a picture in your mind. Earth is rotating from west to east. If the ship was at rest position, ship will also complete one round in 24 hours. But if it also start moving from west to east, it will obviously will complete one round in lesser time. Is it not? If time of revolution is less, omega will increase. And let me put it in word properly. If it is in motion, the omega dash will become more than the normal omega. Why so? Because time of revolution will become less. It is going in the same way, same sense. If omega dash is increasing, in this term, the G dash will decrease than the normal value of the G. If, G double dash, let me put the double dash to make the more thing clear, because G dash is the effective acceleration when ship was at rest. When ship was at rest, when he says T0, this was G dash. And when the ship is in motion, this was under root of L divided by G double dash. Look at this. There's a decrease in the value of G. If there's a decrease in the value of the G, what happens to T? It will increase. So T will be more than that of T0. And if I take this, say, in the spaceship, then what will happen? Suppose I take this pendulum to a space station. What's the value of the G there? Effective G is 0. Effective G is 0. Effective G is 0, the pendulum will not oscillate. If you take a pendulum on one side and release it, it will remain there. It won't come. The time period will become infinite in that case. So there are certain questions of this type. All the pendulum clocks are now out of date, but question can come even from the pendulum clocks. If I take the clock in a mine, have you seen the pendulum clocks? Very old kind of the clock where the pendulum is giving the time, though it's obsolete, but questions are questions. If I take that correct time giving pendulum clock to a mind, will it become slow or will it become fast? Formula is here with you. T equals to 2 pi under root of L by G. Will it become slow or fast? Slow. What happens to G if we go in mind? Decreases. If G decreases, what happens to time? Time increases. So what will happen to the nature of the clock? No, it will move slow because it take more time to cover things, right? So question may be of this type also, but that is through the value of the G. Okay. Yeah, one more. What will be the value of omega of Earth if the apparent weight loss on the pole? On pole, there is no change of omega. There is no effect of omega. Please see this. G dash is equals to G minus R omega square cos square lambda. So for pole, lambda is 90. So this factor is not there. So at pole, the value of the G will remain the G. If any day you find that the Earth start rotating with greater value of omega, then we should move to the poles because the value of the G will remain same there. Whatever may be the value of omega, at pole we are safe, right? But may not be because of the temperature, right? Anyway, so this is how things. Thank you very much.
Hello friends, today we are going to understand the topic chemical thermodynamics in deep details with respect to all the entrance exams and the CBSE course. Now chemical thermodynamics is a term which should be understood well. All the scientific terminologies actually have the meaning in their own terminology. Chemical means it has come from the term chemistry, and thermodynamics. We can break the term and understand the meaning of it. Thermodynamics, where the thermo means the heat and dynamics means its transfer. So it is actually the study of heat transfer from one place to the another. And when we subject it to the chemical reactions, it goes chemical thermodynamics. Though thermodynamics is covered in a physics topic as well, but that is not actually taking care of the chemical reactions, rather all types of systems pertaining to the physical mechanical energy conversions. Fine. So we'll talk about the chemical reactions here, where the chemical thermodynamics is the portion of thermodynamics that pertains to the chemical reaction. So we are going to study the heat transfer from one to another side, where we understand what other aspects and what other things actually happen. Next, please. Now, there are some basic terminologies which actually make us very easy to understand what are systems, surroundings, and boundary. Now, when we understand thermodynamics, whatever we are studying or whatever is under the observation is called as system. It can be a chemical reaction, it can be a jar, it can be a bucket, maybe covered, uncovered, it can be a piston, cylinder, or anything. So whatever is under a study is called as a system. Anything apart from that, maybe the very closest neighbor of it will be surrounding. Anything apart from the system is surrounding. So if we take in together of the system and the surrounding, it is called as the whole universe. System can be as small or can be as big as we want. But anything which is under the study is called as system, and apart from that is surroundings. And together we coin it as universe. Next. So the next, there can be classifications in terms of the systems. We have three categories in the classification of the system. The first one comes up as an open system. Where open system, you can see all these classification actually happen with respect to the transfer of matter and energy. Matter is anything which occupies space and has mass, and energy, you can very well understand there are different forms of energy. So any form of energy transfer would call that as the transfer of energy. So just to make you easy to understand, I have cited some examples for an open system. So open system would be a cup of a coffee. Like you have a cup of a coffee, if kept for a while, later on what happens? Some of the amount is missing because of the evaporation of the coffee would actually take place after due course of time, and also it will become colder in some while. So you can say there is an energy transfer in the form of heat transfer from the system, which is a cup of a coffee, to the surroundings in the nearby place. Alongside, there is also a transfer of the matter. Now coffee has actually reduced. So when there is a transfer of matter and energy, then it is called as open system. Next. The next classification comes to the closed system. Closed system can be anything when you can actually, there is no transfer of matter, but energy transfers do takes place. So you can always take an example, a tightly capped cup of coffee, because now the matter won't actually just spill off. The coffee is intact inside the cup, but still it will become cold after a while. So energy is still getting transferred, but matter is not. So in that very case, we call it such a system as a closed system. Next. The third system classification comes up to be the isolated system. Isolated system is where no matter, nor energy. To be precise, matter can be called as mass, and energy can be actually taken in heat, when we are citing some examples like the coffee in a closed, well-insulated thermos bottle. You can actually keep your thermos bottle for a long time and there won't be any transfer of heat, neither there will be transfer of matter. It can be kept warm for a really long time. So you can say there is no transfer happening with of the matter, either the energy with the surroundings. So system is actually carrying all the energy and all the matter inside it. So that kind of a system is called as an isolated system. So the classification of the system can be open, closed, and isolated. Next. Now, let's come up with an example a kind of an MCQ which has been asked in the exams. Choose the incorrect statement. First, open systems can exchange both matter and energy with surroundings. You have to choose the incorrect one. Closed systems only exchange energy and do not exchange matter with the surroundings. Isolated systems can exchange its matter and energy with the surroundings, and D, none. So very much clear that isolated system actually cannot exchange matter or energy, rather it's been given the other way around in the answer. Right? The next question, a well-stoppered thermoflask contains some ice cubes. This is an example of what kind of a system? A, closed, B, open, C, isolated, and D, non-thermodynamic system. Isolated system, because it's a closed thermoflask where no transfer of energy, neither mass is being transferred. Next. So now we come up to the two different functions which are called as state and path function. Now what are they? As I told you in the beginning only, the scientific terminology has meaning its own terminology. So state function means function which actually depends only upon the state of initial and final state. When we say a reaction is actually starting from here and it is ending to here, whatever process is actually is taking place, whether it follow whichever route or whichever place, it is the state function. It is only dependent upon the initial and the final position of the condition. Like for example, if I have to actually calculate the volume of a water kept inside this bottle, fine. So I am not at all really bothered that where this water came from. I am actually really interested in that what is the initial state and final state. So I am actually depending upon the state what I am considering right now. I am not at all dependent that this water came from the lake, whether it came from the river or it came from the tap, or which country, which area, which city. I'm not at all taking care of the path it traveled to come over here. I'm just calculating the volume. So all these properties which actually only depend upon the initial and the final states and not upon the path covered during this very course of reaction are called as state functions. The other examples can be the internal energy. Okay. Internal energy, enthalpy, and entropy. We'll talk about these terminologies because these are also thermodynamical variables and they have special meaning in case of the basic terminology of the thermodynamics. We'll talk about them in due course. Now about the path function. Path function, as the name suggests, it depends upon the path of the. So like for example, if I have to travel from Kashmir to Delhi, if I come directly from Kashmir to Delhi, then what amount of variable has changed? Like for example, I take up the work. How much work has been performed if I come from Kashmir to Delhi directly? Fine. Other path could be I go to Switzerland, visit some area and then come to Delhi. So it's a longer path I have covered. So the amount of work performed is also changing. It's not the same as I was coming from the Kashmir to Delhi right away. If I go to, you can say Kanyakumari and then come to Delhi. So another variable of magnitude of work is performed. It's not the same as I had actually performed during the Switzerland trip. So as my path is actually changing, every time the value of the variable is changing. So those variables which actually change their value with the path being followed is called as path function. Clear? So there are work and heat. Heat you can understand very well, like I told you, the amount of work performed by me during any kind of travel between Kashmir and Delhi. You can understand the heat transfer in terms of the sweat I actually produced or the heat my body radiated. So you can very well conceptualize the idea that work and heat both are path function because they actually keep on changing their magnitudes depending upon the path being covered during the journey. Fine. So they are not at all only dependent upon the final and the initial conditions, but also on the path traveled. So these are called as path functions. Fine. Now the processes can be actually classified with different types. Now this is another basic terminology of thermodynamics where we say that because the variables temperature, pressure, volume, heat, all these are variables. Though they are interconnected somewhere or the other, but we need to actually constrain. Sometimes there are some constraints that we need to tend to actually keep the temperature constant throughout the reaction. Then what kind of process is it is called as? Or the pressure is maintained constant. What type of process is that called as? So there are some terminologies given to all these words. Let's discuss them. Isothermal. Now, the term iso means same. Fine. And thermal means temperature. As you actually take an instrument called thermometer to measure the temperature. So the term thermo comes up from there. Fine. Isothermal, same temperature. Same temperature means temperature is not going to change. It's going to be constant. So it's going to be delta T equals to 0. Delta T means change in temperature is going to be 0. That means it's constant. There is no change. Fine. So is the next quantity isobaric. Baric actually is the term because long time before pressure was being calculated in terms of bars. So there was the term bar which was associated with pressure. That is why isobaric, same bar, means same pressure. Fine. So same pressure means P is constant. P constant means rest of the parameters may vary, but P won't change under this kind of a condition. So if we actually constitute a condition called isobaric, that means pressure is constant. Rest of the variables may or may not change. We are not at all actually considering that. But pressure is not subject to change because we have stated isobaric. Isobaric means same pressure. Fine. So delta P goes to 0 here because delta P means change in pressure. Delta means the difference between the final and the initial condition. So delta means final minus initial. If final minus initial terms 0, that means there is no change in the final and the initial condition. That means there has been a constant value throughout. So that is why delta P goes to 0 means that pressure is constant throughout. Clear? Now the next third terminology comes isochoric. Choric word is actually associated with the term volume. Right? Same volume. Same volume means that V is constant. And similarly, delta V also goes to 0. After these three terms of being pressure, temperature, and volume constant, we come up to another term which does not start with the term iso, rather means adiabatic. Adiabatic because these are the system in which heat transfer is 0. That does not imply heat is 0 because many a times heat is written as zero. I do not state delta for heat. Now there is a specific reason for this. Why do I not state delta for heat? Because the value delta means the change in the final and the initial condition. Clear? But we can only constitute the value of final and initial conditions for those variables which are only dependent on that. That means the state functions. Temperature, pressure, volume, internal energy, enthalpy, entropy, Gibbs free energy, all these are state functions. So we can actually put the delta above them because these are the state functions which actually depend upon the final and the initial condition of that very process. But as I told you, work and heat are the path functions. That means they actually really do not depend upon only the initial and final condition. Like I stated the example of traveling from Kashmir to Delhi, I took 3 different routes where I traveled directly from Delhi to Kashmir to Delhi, taking the shortest distance. Thereafter, I traveled to Switzerland and came back to Delhi. And another one when I visited Kanyakumari and came back to Delhi. So all these are different, though the initial and final positions are absolutely the same in all the 3 cases. But the amount or the magnitude of heat and work released or absorbed is different in all the 3 cases. So that means it's not at all only dependent upon the state, but the path. So that means a word delta, or you may say the difference between the initial and final cannot be constituted because every time the answer is going to differ. So we do not have the delta value for the change or the transfer of heat. That's why when I constitute the delta value for pressure, temperature, pressure and volume, I cannot do the same for Q. I cannot write delta Q because it's a path function. So it cannot have delta value. It has to have a partial differential. Fine. So the another terminology which comes up is that all state functions are exact differential. Exact differential is where they depend upon the final and the initial condition. And the variation can be measured with the difference between the final and the initial state. Fine. However, path function cannot, because the different three routes may have different magnitude, although the final and the initial destinations were same. Still, we do not have the same amount of work and heat coming up in all the three cases because they depend upon the path as well. We cannot constitute the change or the transfer in terms of delta W or delta Q. Understood? So path functions do not have the delta term above them. Or you can say we cannot write delta W or we have delta Q. But some terminology has to be there. How to actually confirm that heat transfer or change in heat, how to actually really come up with the term change in heat, because change is actually happening. So that term cannot be constituted with the delta in the triangular form. It is taken as a del form, where this is called as delta and this is termed as del. Though both constitute the meaning for the change, that is the difference. But the delta term is suited for the state functions and del for the path functions. Fine. So we say the adiabatic system in which no heat enters or leaves the system, that means del Q is 0. That does not mean Q is 0. Heat must be there inside the system. Maybe positive or negative, but there is no transfer from the surroundings. Neither it's taking it up nor it is giving it up. Fine. So is the case with the rest of the terms also. Temperature is constant. That does not mean temperature is equal to 0. There must be some temperature, but it is not changing. It's not varying. It's same. So is pressure and volume. And the adiabatic condition means in which there is no heat transfer, neither heat enters nor heat leaves. It's the same intact. So you can say a thermoflask is a kind of an adiabatic system. It's not moving, excuse me. Yes. Now we come up to the another terminology of thermodynamics, which actually assign the properties of a system. We have classified the system in terms of open, closed, and isolated. Now we move to the properties of a system and the variables. The properties of a system is a measurable characteristic of a system that is in equilibrium. Now, properties may be extensive or intensive. Properties of a system means the system may comprise of some variables, like it has some volume, it has some pressure, it has some density. Whatever the quantity or the substances I am comprising inside the system, it must be having some properties which actually signify its state. That what is its temperature? What is its pressure? What is its refractive index? Maybe its density, maybe its volume. So all these are the properties which signify specificity of that very system. So these properties are actually described in terms of being intensive or extensive. Fine. Intensive properties are those which are independent of the amount of mass. Amount of mass. Now, this is the most important terminology. And obviously, the extensive are the opposite of the intensive, which varies directly with the mass. What do you understand about the mass thing is, like for example, I say I have a system in which there is some amount of substance. It has some properties. So for example, it has some mass, it has volume, it has temperature, it has pressure, and it has density. This is the rho which means density. Fine. Now this system is having certain boundaries. What happens to all these properties if I actually vary the mass? Vary the mass means I take out some amount out of this very system. So what I did, I divided the system into two divisions, maintaining this as one system, the other one as the other system. Fine. So what I see that this system has actually varied the mass now. It has become half the value of its initial value. Actually, parting, or you may say taking out some quantity of mass out of the system has actually reduced or changed or varied the mass volume, but it did not do for the temperature. Like for example, I take a bucket of water, and that bucket of water has ice cold water into it. So it's not ice, so it may be having ice cold water means maybe 3 degrees centigrade of temperature or 4 degrees centigrade of temperature. In Kelvin, the transformation would be 273 plus 3 if it is a 3 degrees centigrade temperature. So it will be 276 Kelvin. Fine. What happens if I take out some mass of water? Like there is a full bucket, I take out like half a liter of water has been extracted from it. Does temperature change for the remaining water in the bucket? No, it's the same. That means it has nothing to do with the variation of the mass. If I take out some mass or some amount of the matter, it does not change. If it does not change, it is called as intensive property. But what about other properties? Like say example volume. I took 5 liter of bucket and I filled it up to the full level. I took out half a liter of water out of it. Now the remaining volume is not the 5 liter. It has changed. It has come to 4.5 because 5 minus the half the liter of the volume of the water, it is 4.5 liter of water remaining behind. So earlier it was 5, now it is 4.5. So varying the mass, the quantity is changing. That means it is called as an extensive property. Fine. So intensive and extensive, you understand. Those properties which are independent of the amount of mass are called as intensive properties like temperature, pressure, and density. Extensives are the ones which varies directly with the mass. Mass, volume, energy, enthalpy. So if we actually extract out some mass, all these parameters are going to change. Like say, mass has actually got half by parting the system into half. Volume has also got changed, but not the temperature, neither the pressure, because that is uniform throughout. I have just created a wall in between. So the pressure in both the compartments is going to remain the same as it was originally in the previous system. So pressure is also not changing. So is the density. If you just want to understand whether it is an intensive or an extensive property, just think of the example I just gave you of a bucket of 5 liters of water. What happens to that very property after taking, you can say, a liter of water or maybe half a liter of water out of it? Does that value change? Does the density change? No. Does the viscosity change? No. Does the mass change? Yes. Number of moles of water changed? Yes. So this is how we decide whether it is an intensive property or an extensive property. Though it's very important to remember the term intensive and extensive, because intensive, as we say, internally we do not change. Just to remember and keep it in your mind for the exam point of view. So because the two terms actually sound very close and you don't mix up and write the other way around. Intensive sounds like internal. Internally we never change. Extensive sounds like externally. Externally we keep on changing. We keep changing our clothes, we keep changing our moods and all. But internally we are the same person. So the intensive properties are independent of mass and do not change with the mass, as we do not change internally. But the extensive quantities will change as we change externally. So just to remember and not to actually write the vice versa, remember that intensive do not change, like internal systems do not change. Your heart remains the same position, your kidneys function the same condition. They do not change with the external environment. But externally you change. So the extensive property is which change with matter. After that, let's come up with a brief questions. Which of the following is not a state function? Now, state function is what? Depends upon the initial and the final state of the condition. State function, first is entropy, second is volume, third is enthalpy, and last is heat. That's heat, because I just stated in the example that all the other variables are state function. So heat is dependent upon the path traveled. As long as it goes so, it cannot be coined as the state function. The next question, identify the intensive quantity from the following. Now the intensive, as soon as the word comes, remember intensive do not change. Internally do not change. So intensive, internal do not change. So it should not change with the mass or the amount of the substance being changed. Enthalpy and temperature. Now you need to actually come up with the combination. So one may be intensive, the other may not be. So you have to be very much clever and quick with it. Enthalpy and temperature. Temperature is obviously an intensive property, but enthalpy extensive. So this may not be the answer. Volume and temperature. Volume is extensive. So we can strike it out here itself, because identify the intensive quantity. So both the combination should be intensive. Even if one is not intensive and you are dead sure, leave that very option. Move to the next. Enthalpy and volume. Both are extensive. Temperature and refractive index. Refractive index does not change with the amount. If I actually shorten the, you can say glass slab, refractive index would not change. Fine. So the answer is D. Next. Now some more questions to brief you. Identify the extensive quantity from the following. Extensive, that means change with the amount of the substance. Boiling point. Will it change? No. Viscosity, it won't. pH. Will pH change? It's uniform all throughout. It's uniform. So it does not matter if I take some amount of that pH will remain same, because it's actually uniform throughout. So if I make a partition inside the bucket also and I treat it for the half side of the bucket, pH will remain same. Fine. EMF of a cell. Now EMF of a cell, according to the Nernst equation, if you guys remember, is dependent upon the concentration of the products and the reactants. So if I take out some amount of the substance, it may vary the concentration of the product and the reactant. So EMF would change. Fine. And the last goes molar heat capacity. Molar heat capacity is amount of heat required to raise the temperature by 1 degree centigrade for 1 mole of a substance. So if I take up some amount, it will change. So what are the quantities? What combination we should go for? Identify the extensive quantities from the following. Is it 1, 2, 3, 2 and 5, 3 and 5, or none? Extensive quantity from the following. It's none. Because though we have set of extensive quantities inside these combinations, but the combination hasn't been striked out here. Clear? Okay. Next question. In an adiabatic process, adiabatic, just remember, heat transfer is 0. But there are the 3 confusing terms given to you. You have to be very thorough that what does that mean? Like I said, adiabatic means heat transfer is 0 and heat is not a state function. I cannot put delta above it. So this has been striked out. Next, heat is not 0. Q equal to 0 is not correct. Heat may be there. Sum of magnitude is going to be there, but the transfer is not feasible under adiabatic conditions. So for that, del Q is equal to 0. So the option to be struck is D. Clear? Next. Now we come to the next, heat and work. These are the terminologies we have already talked of, and we will talk in details about them now. Work to be taken first. Work is in mechanics is displacement against a resisting force. So that is what you have studied till your previous classes, where work is nothing but force into the displacement in mechanical terms. Work has units equal to joule because work is also stated as a form of energy. So it has the same unit as joules. It's the SI unit, which is joules. Cgs unit is calories. And the conversion of calories into joule is 1 calorie is equal to 4.18 joules. Now, work can be expansion work, where we say it has to be P delta V. The expansion work is called as P delta V, where the P is the pressure and delta V is the change in the volume while considering the expansion. Like for example, I had a piston. This is my system where this is the volume V1. I brought about some expansion and piston has been moved outwardly. So my new volume would be V2. So my delta V is V final minus V initial, that is V2 minus V1. So delta V would be the change in the volume brought about during expansion course. And P is the external pressure, because the external pressure decides that how much expansion will happen. Fine. So P delta V is the external pressure into delta V. Why external pressure and not system's pressure? Because when the expansion happens, it happens because of the outside. Whether piston would actually expand or compress depends what is the pressure outside, because we all have a condition of coming in equilibrium with the surroundings. Like for example, when you go to your college, or your school, you actually design yourself according to the conditions in the surroundings of the school. You prepare yourself mentally, wear a uniform and go to school. So is the case when you go to a party. You dress like, when you actually have to go to a party, you dress differently. So you actually create yourself or prepare yourself according to the conditions of the surroundings. So is the system. Like for example, you are a system and you are going for any kind of the processes of a party or maybe school or maybe to sleep. You actually design yourself for that very thing. You make variations in yourself according to the surroundings. So is the system. But what decides that what to do? Whether you have to change to a party cloth or to a bedtime cloth, that depends upon the surroundings where you are actually going for, what process you are falling for. So in that very case, it's not the system's pressure, it's the external pressure, surroundings pressure, which decides whether the work done is to be in terms of expansion or compression of a piston. Understood? Fine. So this pressure is going to be the external pressure. And delta V will obviously be the system's volume after the course of expansion. Clear? The change in volume. Electrical work, magnetic work, etc. There are many stimuli to the different responses for the work. There can be different kinds of work. But let's not actually just go in details of others and remain with the expansion work. Because we are going to talk in terms of the chemical reactions, we are going to assign some sign to the work. Because we know whether the work is done by the system or on the system, this cannot be constituted by any of the magnitude. Though the amount, the value of the work will always give you the magnitude of the work, whether done by the system or on the system. But how to actually write it? I cannot write work done on the system every time. So for this kind of a notation on the system or by the system, to make it very clear, I use sign notations, which has been used worldwide the same. So there is no problem if I use minus for the either of the signs, but there is some rule and regulation to be used worldwide, because if I had to put a negative sign, I have actually put it up on a positive sign. When I make a calculation, I may end up with a different answer. So you can say universally it has been noted that the sign convention when the work is done on the system is positive. Fine. And when the work is done by the system is negative. Whenever work is performed by the system, it is negative. And when this work is done on the system, it is positive, though the quantity is described by the magnitude. But whether system is performing work or the work has been performed on the system is coined by the sign convention. Fine. Now, how to memorize these sign convention? Because it's very difficult to remember. We may actually get confused by the time we actually come for the entrance exam, whether it is negative for the work done on the system or by the system. So just to remember, for a quick, you can say remembrance, always remember that system is very special and it is just like a guest. Like you are not supposed to actually make your guest work at your place, as our system says, as our culture says, Atiti Devo Bhava. System cannot perform work. It's a real, you can say, disgrace to your house if your guest comes to your home and performs any chore or job. Fine. What you say? Let me do this. You are always there for your guest. So when you perform a job for your guest, it's a positive thing. And when a guest performs, it's a negative thing. So is the system. When systems perform any task or any work, it is negative. When work is done on the system, it is positive. So a quick, you can say, mashup for remembering terms, not to get confused with it. Work is done on the system is positive. System is guest. If work is done by the system, it's negative. It's not nice to get your system working on it. Okay? Now we go to the heat, the another form, where we say the transfer of energy between system and surrounding as a result of the temperature difference. When the temperature varies, if there is a colder body kept in the surroundings of a hotter sub-surroundings, what happens? The temperature difference is there, so heat will transfer from surroundings to the system because it transfers from hotter to colder. If I have a hotter system and the surroundings are really cold outside, my system will start releasing heat to the surroundings. Fine. But also we have some magnitude for the amount of heat, but we need to put up similarly as we did for the work, some sign convention whether heat is being absorbed or released. So similarly, if heat is absorbed, that means system absorbs heat and performs work. That is an endothermic reaction, as it is done in the endothermic reactions. Because we know that in endothermic reactions, heat is provided to complete the course of reaction. And in exothermic reactions, it's other way around. Heat is released. Clear? So when heat is absorbed to perform a reaction, a chemical reaction, it's an endothermic reaction, Q is positive. It's treated to be positive. Clear? And if heat is released means it's in the product side, then it's exothermic reaction. And such a case, we call that Q is negative. Just to remember, always remember Q is negative when heat is released. As you know that nowadays global warming is a very negative aspect going around. A lot of deforestation, industrialization, pollution has led to it. And global warming is leading because of the rise in the heat on our environment, or you can say the earth is getting heated up. A lot of posters, banners you can see, and it is a negative aspect going around. So it is because of the heat release. So we say it's negative. So remember that heat release is always negative. It's just for a short review, you'll always remember terms and don't confuse between. So heat release is always negative as it is in the global warming aspect. Fine. Heat absorbed is positive. Obviously, the other way around would be positive. If heat gets absorbed, the effect of global warming will actually substantially get loosened up, so it will be a positive aspect. Clear? Okay, next please. The next terminology which comes up is the internal energy. As the name suggests, internal energy, it is not at all comprising about the total energy we had been actually counting on, the kinetic, potential, or any other mechanical energy. It is the internal energy. Internal energy means internal, your system's internal energy. What is going inside the system, not what is actually it is behaving on the outside. The energy which it is having itself. You know that the system is made up of matter, and the smallest unit of matter is atom, and which can be subatomically called as proton, electron, neutron, where proton and neutron are actually inside the nucleus and electrons are revolving around the nucleus. So there may be some interactions going around inside them, which is actually comprising the energy. There is translation motion of the electron. There is vibration motion of the electron, where it vibrates like a spring. There can be rotational motion of the system. It can be rotating just as Earth rotates on its own axis. So lot of different interaction. There can be electronic and nuclear interaction. There can be electron-electron repulsion reactions. So lot of reactions going inside, because of which lot of energy coming out. And the sum of all these sorts of energy, total coin as internal energy. Fine. So you can say that absolute value of internal energy cannot be determined. This is because system has lot of atoms, and all those atoms have lot of electrons, protons, and neutrons. And these are subatomic particles which cannot be seen by the naked eye. As we know that if we get an instrument to calculate the translational energy of a system with a very next fraction of second, because electron is a very fast, randomly moving particle in an orbital. It keeps on changing every time its translational energy. So as soon as I actually gather the data to calculate the exact value of the translational energy, I miss out on the rotational part. I miss out on the vibrational part. And even if I do so, the very next amount, it changes its electronic value or the nuclear energy value. So it is very difficult rather I should say, it is impossible to calculate the exact amount of the total energy coming because of all these kinds of reactions going around. Because there are multiple kinds of reactions going around, and all through simultaneously at a subatomic level, that is the microscopic level, one cannot calculate. So the exact amount of all the sum of all these energies is not possible. So we say internal energy cannot be calculated exactly. We cannot have the exact value of internal energy of any system. But what to do now? If we do not have the exact value, still we have to come up with something to go around with the other calculations. So in that very sense, we say that absolute value of internal energy cannot be determined because it is the sum of the electronic, nuclear, chemical bond energy, kinetic energy, potential energy, etc. So many sorts of energy, some of which cannot be determined accurately because of being at the microscopic level. So we say we find out the change in internal energy, which is delta U. If the final is U2 and the initial is U1, we say delta U is U2 minus U1. But still we do not have the magnitude for U2, neither for U1. These are the exact initial and exact final internal energies. We do not have the values for the two. But we can figure out the delta U. How it is possible when we do not have U2, neither we have U1? How can we get the delta U value? The internal energy change is the heat absorbed or evolved at constant volume. At constant volume, we say that the change in internal energy is equal to the heat absorbed or evolved. But that constraint comes only when there is constant volume. So delta U can be calculated if we find the heat evolved or absorbed. That can be very well done with the practical instruments we have at constant volume conditions. The sign convention goes the same as we go with the heat because it is coining as same as heat. So the energy absorbed, delta U is positive. Energy released, delta U is negative as the sign convention was used for heat. Since we are stating delta U equal to heat at constant volume. Fine? Next, please. Now, it's absolutely fine to calculate the heat under isochoric condition. That means under isochoric means volume constant conditions. But what about those conditions where I do not have the constraint of constant volume? In generalized term, I say I need to have certain demarcation for that. And here we constitute the first law of thermodynamics. So we start with the laws of thermodynamics, where the first law says that the internal energy of an isolated system is constant. Isolated system is constant because there is no heat being dissipated or being absorbed. There is no work or any kind of part of energy being transferred to the surrounding. So whatever is there inside the system is intact. So internal energy of an isolated system is going to be constant. Clear? There exists a state function. Internal energy is used for the subscript in many of the entrance exams and books as U as well as E. The capital U or E, both are absolutely acceptable. So you may use either of the two. Not to confuse with the electrical or EMF values, I will be using U. But it is absolutely fine to be asked in terms of capital E. Many a times, internal energy is asked in terms of capital E in the entrance exams. Also, capital U. They both are acceptable, absolutely. Fine. We will be using the U notation further on. Now, there exists a state function. State function means it depends only on the initial and the final condition, and the path travel is not at all a botheration. U or E such that for any process in a closed system. Now the system is closed. That means there may be transfer of the energy, though the matter is not getting transferred. If energy is getting transferred, obviously the amount of rotational translational energy is going to change. All these energies which are comprising of the internal energy are going to change. But we cannot find the exact amount of the internal energy. So now what to do with the change in internal energy? How to calculate that? Because we do not have a constraint of constant volume also. It's a generalized term. So here we say that change in internal energy is nothing but sum of the heat and work. Because whatever amount of energy it must have gained from the surroundings or must have lost to the surroundings must be in the form of work or heat. The internal energy change has been brought up at the expense of amount of heat absorbed or evolved or work done by the system or on the system. That means that internal energy, when the system was in the initial condition, it had some value of internal energy, though we cannot find it out. Let's say it's U1. But after a while, it actually went through some process. It must have released or absorbed some heat. It must have performed work, whether it is done by the system or on the system during that course. And later on at the final condition, we need to figure out the final internal energy. It has changed because of the due course of transfer in the form of heat and work. But I do not know that what is the delta U, because U2 minus U1 I cannot constitute. But yes, whatever has been the change, it is because of the transfer to the surroundings in the form of work and heat only. Else, had it been an isolated system, it would have been intact and there had been no change in the internal energy. But internal energy is changing because of the transfer to the surroundings in the form of heat and work. Maybe the loss or maybe the gain in whatever form. But the variation in the internal energy has come up because of the work and heat. So you can say the change in internal energy is nothing but the sum of the two. Whatever loss or gain, whatever performed by the system or on the system. So in that very case, we coined the mathematical statement of our first law of thermodynamics, where we say delta U or delta Q is equal to Delta E is equal to Q plus W, the amount of heat and work being transferred. Gain or loss, work done on or by the system. Both. Fine. So delta U will be actually amount of heat and work being transferred with the surroundings. Where Q is the heat flow into the system, W is the work done on the system. Or it can be other way around, where Q can be the heat flow out of the system and work done by the system. Either way or the other round. Fine. Both are acceptable. Q and W are not state functions. They all are path functions. However, the two path functions are together adding up to define a state function. Fine. So this is the beauty of this first law of thermodynamics, that both path functions describe the state function. Now, the change in internal energy of the surrounding will be opposing in the sign, because whatever has been lost by the system will be the gain of the surroundings, and whatever has been gain of the system is due to the loss of the surroundings. So you can say the change in total of the system internal energy and surrounding internal energy is going to be zero, because if I say that some amount of work and heat has been lost by the system, where did it go? It went to the surroundings. So there has been a positive sign for the heat and a positive sign of the work for surroundings, but the negative for both for the same magnitude for the system. So adding together for the system and the surrounding, the total sum would be cancelling and we will result with a zero. So the change in the system's internal energy and the surroundings internal energy taken together, because they both are actually changing at the expense of each other. If this one is gaining, this is gaining at the expense of loss of the surroundings. If surroundings is gaining, it is gaining because of the expense of the loss of the system. So together it is going to be zero. Clear? Next please. Is that clear? So we move to the next slide where we have some brush up questions. First, in a stoppered closed container, a liquid is stirred with a paddle to increase the temperature. Now temperature is being increased, but do not forget stoppered closed container. It's absolutely tightly closed. So what do we expect here? Delta U and W are going to be equal and not going to be zero. Q is going to be zero. If it is a stoppered flask, that means we do not expect the transfer of the heat. That means Q is going to be zero. Here we are actually ought to take the del Q here. That means that the change in Q is zero. Fine. We haven't stated the W and Q as the change, but here we, in this very specific question, we actually mean the change in work and heat. So there is change in heat. So Q equal to 0 would actually comprise for the del Q equal to 0. So there is no transfer of heat. However, work and internal energy are not going to be 0, because we are paddling the stirrer inside the thermoflask and it is some work is being performed. It's not zero work we are actually performing over it. And due to that work, some internal energy is going to change. Remember the first law of thermodynamics? Delta U is equal to Q plus W. However, Q goes to 0 because the thermoflask is absolutely an isolated system. So there is no transfer in the heat. But because of the paddling of the stirrer, which we are doing, there is some work being performed. So delta U is definitely going to have some unit, because the first law of thermodynamics says that delta U is equal to W, that is del U, W plus del Q. This goes to 0 being an isolated system or a thermoflask system. However, del W is not 0. So delta U is not going to be 0, rather equivalent to the 2. So in this case, we say the next case, delta U is equal to W is equal to Q, which cannot be true. The other case says delta U is equal to 0, W is equal to Q. Internal energy change is not 0 in such a system because system is isolated, no fact. But we are paddling the stirrer as well. So we are performing some work. Had it been in a stationary condition, delta U would have been 0. And the fourth option, W is equal to 0, which cannot be because we are paddling a stirrer. We are performing a work over it. So what is the answer to the option? A. The next question, internal energy does not include. Now the internal energy is system's energy. That means what system governs in itself. Could be at the atomic or subatomic level. So let's strike out the odd one out, which is not the case. Vibrational energy is system's energy, as we just discussed. Rotational is also. Energy arising due to the gravitational pull. That is because of its surrounding, not because of the system. The gravity comes at the surrounding level of the system. Nuclear energy. Nuclear energy is the energy of the nucleus. So again, this is system's energy. So the odd one out to be striked out is option C. Next, according to the first law of thermodynamics, delta U is equal to W plus Q. Delta U is equal to W minus Q. W is equal to delta U plus Q or none of the above. A. As stated, it's very much clear that delta U, that is the internal energy change, is always at the expense of Q and W. Though the point to be mentioned here is that I just noted the sign conventions for Q and W. There may be cases that heat is getting released, but still the same formula is to be constituted because this is without the sign convention being used. Though it is system specific quantity to signify the sign convention. In case of heat release, Q going to be negative. In case of heat absorbed, Q is going to be positive. In case of work being done by the system, W is going to be work is done by the system, negative. If work is done on the system, positive. So those sign conventions are to be used later on. But first of all, put this formula in itself like this as well. Later on, W may become negative and formula may change depending upon the kind of system, processes and conditions. But the fundamental formula goes this ways only. For your numerical purpose, always remember the first law of thermodynamics constitute in this manner only. Next, please. Now, we talk about another kind of a process, that is the reversible and irreversible process. It's very well known to all of you because this is a literal word, reversible and irreversible. Anything which can be reverted back is reversible. And what cannot be reverted is called as irreversible, which is according to its literal meaning. But in thermodynamics, it has something to add on to it. What does it go to? A reversible process is one where an infinitesimal change, infinitesimal means very small change, fine, in the condition of the surrounding leads to reversal of the process, fine. And when an irreversible process, the reversing the condition process can be reversed if it is carried out rapidly. I'll just clear it out apart from the definition, what is reversible and irreversible process. Like for example, you know that systems keeps on changing to come in equilibrium with its surrounding. So whatever variable it has in its own systems, it's going to come in equilibrium with the surroundings variable. Like system had a temperature T and the surroundings temperature was T minus del T. Del means a very small difference, but still it would like to come in equilibrium with the surrounding. So here there will be the temperature flow from inside to outside because inside it is a higher temperature than the outside. So temperature will flow from inside to outside, but it will be a very small amount. The infinitesimal amount difference is to be maintained. Fine. So in doing so, it may happen that infinitesimal amount has been transferred in addition to the del T. So now the condition becomes the other way around. It has become T plus del T and temperature is T. Now the heat transfer will occur from the surroundings to the system because the difference in the surroundings and the systems condition was very infinitesimal or very small. So that is why the condition of moving from system to surrounding or surrounding to system will keep on doing as the difference is really small. Because as I move from system to surrounding, it may happen that I actually aggregate the condition of infinitesimally at the surroundings part. Then again, the system has to revert towards the system. So the condition has to revert towards the system from the surroundings. So this kind of a case goes reversible, where there is only variation of infinitesimal quantity. Fine. However, in the case of irreversible system, here is an example I have cited, where there is 40-degree temperature of the system and surrounding has 80 degree. That's a huge difference of 40 degrees centigrade. 80 minus 40, that means the gap is huge. So what will happen? Because the outside body surrounding is hotter, system is cooler, the heat flow will happen from the outside to the inside. But to what quantity? A very large quantity. So it will keep on happening as soon as there is an equilibrium between the two. And it won't revert back until it is actually being transferred to an equilibrium condition. So it is moving rapidly because there is a huge amount to move on and it has no mean to move back. Lee-Chatterjee principle does not allow it to. So in that very case, it will keep on moving towards this direction and it will keep on moving rapidly and for a longer duration, unlike the irreversible condition. So this is why this is called as irreversible condition. When there is a huge difference between any of the variable of the surrounding and the system condition, the system is going to be irreversible. And when there is an infinitesimal change in the variable of the system and the surrounding, it's going to be reversible system. Here I have cited an example of temperature. It can be in terms of pressure as well. That the external pressure is infinitesimally small or large than the system's pressure. Then it's going to be a reversible case. But if the difference is going to be huge, then it's going to be an irreversible change, because maintaining that huge difference, you have to be constantly moving towards your equilibrium condition, and that's going to be rapid. That's why it's called as an irreversible system. Understood? Okay. Now, since it's reversible system, the process keeps on moving. Like reversible, what happens? Temperature is moving from system to the surroundings. Later on, it takes its own take from surroundings to system. Again, it's going to be in this condition. So there is a movement of heat flow from surroundings to system, system to surrounding and all. So the maximum work will be done if the compression or expansion is carried out in a reversible manner. Also, I just told you that the work done during an expansion or compression is P delta V, where delta V is the change in the volume. Could be because of the expansion, where V2 is the final and V1 is the initial. And could be because of the compression, where it's going to be V1 minus V2. The final condition would be the V1, the smaller one, as I gave example over here. But this pressure is which pressure? External pressure, not systems pressure, because that is what is going to decide that how much amount of work is to be done. External environment decides what amount of work is to be done by the system, because it has to come in equilibrium with the surroundings. So this pressure is not systems pressure, it's external pressure. Fine. So when we coin here, the maximum work will be done if compression is carried or expansion is carried out in a reversible manner. This is because the difference, this P external, is going to be really huge in case of the reversible system. That we will take up when we will solve for a system in the later slides. But I hope you understood the reversible and irreversible system. Any quantity having a huge difference between the surrounding and the system is going to be an irreversible system, where there is an infinitesimal change, maybe temperature, pressure of any other quantity of the surroundings and system, then it's going to be a reversible system. Next slide. Now, we actually come up with the work done for an irreversible process. For a gas taken in a cylinder fitted with a frictionless piston and expanding from a volume V1 to V2, as I showed you here, this is a piston, here is a gas, this is the volume V1, it's being expanded to volume V2. Against a constant external pressure, like for example, if I say there is an external pressure P external, which is constant all among the surroundings, then the work done in an irreversible process is W is equal to P delta V, where P is the external pressure. Since it's an irreversible process, P external is either going to be very, very large or very, very small than the P system. Irreversible process, the difference is going to be huge. So that is why when we actually have del W equal to P external delta V, we integrate both the sides. The mathematical calculation is not in your course, but I'll just giving you a kind of a understanding so that you don't have to mug up that how did it came. Just understand, you need not to understand how the integration took place. It's W equal to P external, delta V would become, where this delta V is del V, will become V, and putting up the units of V1 to V2 would become V2 minus V1, as stated here. Since it is being coined as the work of expansion, a negative sign convention would come up, because whenever expansion of a piston happens, the work is done by the system, because system is actually expanding the piston to move outside. However, whenever a compression happens, one has to push it from outside the surroundings to go it inside. So expansion is always work done by the system. That is why sign notation would be negative. And compression is work done on the system. You have to push the piston inside. Even if the gas compresses itself, the piston will remain here. So one has to come out from the outside surroundings and push it inside. So it is, the work is done by on the system. So W will be positive. Fine. So that is why the sign negative notation has been used here. However, the work done for isothermal reversible expansion. Now reversible, this is for the irreversible one. If I take the reversible case, now I know in the case of reversible P external is infinitesimally small or greater than the system's pressure. So I say not equal, I haven't put this sign, but approximately same. So I am taking an approximation that the both are absolutely same. In doing so, I assume that the gas inside is in an ideal gas. And I bring out the calculation where I say dW is equal to, instead of writing P external, I can write P system. Since P external and P system are same, I put up the P external as P system. And when I bring about the integration, now I know inside there is an ideal gas, and ideal gas has to follow a equation of PV is equal to nRT, where the P is the system, or you may say gas pressure. So where I can equate P is equal to nRT by V. In doing so, I guess nRT by V dV, and when we integrate, we get W is equal to nRT natural log. If it's an expansion, V2 upon V1. And negative sign comes up because of the sign convention of the expansion work. So here we get minus 2.303 value has come because natural log has been converted to the log base 10. Fine. So 2.303 nRT log of V2 by V1. In terms of pressure, it would be P1 by P2. Fine. So now you have a basic understanding, although it would have been actually not sounded very well that how these terms came up. Why we actually constituted the different values of work in case of reversible and irreversible, only because of the definition that there is an infinitesimal change in the variable of the surroundings and the system in terms of reversible system, and huge difference is going to be there in terms of irreversible system from the system and the surrounding. Because of these, the two different values are differing to a huge level. Clear? And we figure out that the value coming out in the reversible work is greater than the irreversible work. Fine? Okay. Now, negative sign has been used for the work of expansion, that is work done by the system. This also you have understood. Expansion against a vacuum. Against a vacuum means that surroundings is actually comprising out the vacuum space. Vacuum means there is no pressure. P external goes to 0. If I put my system inside a vacuum, what will happen? External pressure is absolutely 0. Inside there is some systems pressure. Let's, for example, understand this. When external pressure goes to 0, system is actually having some pressure inside it. Let's say P system, which is anyway going to be greater than, because we cannot create pressure in negative values. That means 0 pressure is the least of the value. And whatever value, even the 1 atmosphere, 2 atmosphere, 100 atmosphere, anything is very huge in terms of the external pressure going to 0. In that very case, we say that external pressure and system pressure has a huge difference. And to create that equilibrium condition, this pressure has to go down. That means it should reduce to come in equilibrium with the surroundings. So to come in equilibrium with the surroundings, this has to reduce. How will the pressure inside the system will reduce? By the course of expansion. And obviously the difference is huge between the surrounding pressure and system's pressure. So it's going to be a very rapid and unending kind of a motion. So just like you feel in a lift, free falling lift, when you actually fall freely out of the force of gravity, the same feeling the piston will feel, because it will actually move freely under the condition of free expansion. So the expansion is going free because it has to come to the surroundings pressure. Let's say, for example, it has 1 atmosphere also. It cannot come and stop over anywhere, because in that very condition, it may comprise of 0.1 atmosphere or 0.001 atmosphere, which is not 0 atmosphere. If I have to constitute 0 atmosphere, the piston has to go off and gas has to come up in, you can say, contact with the surroundings. So under the condition where we say that P external is 0, that is the system is kept inside the vacuum, the work done will be 0, because work done is nothing but P external dV, where P external is 0. So what is the work done? Whatever value dV may be, but P external going to 0, W is itself going to be 0. So work done will be 0. It's an isothermal condition, free expansion, as we stated. So isothermal means delta T going to 0, and delta T with respect to delta U actually comprises delta U equal to 0. That we will take up in the heat capacity unit in the later slide. Delta U goes to 0. First law of thermodynamics says delta U is 0, work done is 0, so automatically Q is going to be 0. According to the first law of thermodynamics. If both the quantities are 0, the third quantity has to be 0. Clear? Okay. So this is called as free expansion whenever the system is kept inside in a vacuum condition, because the external pressure goes to 0. The next comes comparison of reversible and irreversible adiabatic work, where we say that for reversible expansion, as P external has maximum value, only infinitesimally smaller than the system's pressure. Work done in reversible expansion is maximum work for a given change in volume. because the amount is the maximum in the reversible case. So that is why that in the reversible expansion, P external will be having the maximum value. So out of the reversible and irreversible, reversible process has more amount of work being performed. And you can note it down from the values also. You can see very clearly that reversible work has a bigger quantity to come up with. Clear? Next slide, please. Now, the next variable we need to talk about, the quantity, the thermodynamic parameter, is enthalpy. Like I said, internal energy is the energy of the system. Now, what is enthalpy then? Enthalpy is also system's energy, but it has something in addition with the internal energy, because enthalpy is subscripted as capital H, where we say it is the sum of internal energy plus PV, where we know that PV is the amount of work. We have actually constituted P delta V many a times for the amount of work. So it is the sum of internal energy and work. Now, which work we are talking about? It's the energy of the system, which comprise of the total energy, that is internal energy, and the amount of work done by the system to come in equilibrium with the surroundings. PV is the work which has been done by the system. Like for example, I tell you, I give in a very easy manner for the understanding what you comprise inside the your system. There are a lot of biochemical reactions going on. Your heart is pumping, your respiration is actually giving you some amount of energy, ATP loss and all those. So all that is your internal energy, which is because of your own system's energy, the reactions going inside the system. Similarly, the reactions at the subatomic level in the system may be the vibrational, rotational, translational, all those nuclear electrostatic energy, all those are comprising of the internal energy. But when you are kept inside a surrounding, let's for example, in a classroom, you come in the equilibrium with the classroom. Whatever energy you must be having your own, plus you come in the equilibrium with the surroundings. If you go to a party place, you change your energy criteria. Like you, for example, you dress up accordingly and you change yourself according to the surroundings of a party. You go to bed, you change yourself to come to a sleep mode. You change your energy according to the surroundings. So the sum of internal energy and the amount of work done by the system, which is PV, by the system to come in equilibrium with the surroundings is called as enthalpy. So it is addition to the internal energy that it coins as total energy of the system. Understood? So enthalpy is internal energy plus amount of work done by the system to come in equilibrium with the surroundings, to settle it up somewhere. Fine. The system also comes in equilibrium with the surroundings. Whatever kind of surrounding conditions are, it comes in the equilibrium. So the total amount of work done by the system to come in the equilibrium plus system's internal energy taken together is called as enthalpy. And mathematically it is stated like this. Now, the problem is, since we cannot actually calculate the exact amount of internal energy, because there are a lot of reactions going on, we just stated that exact internal energy cannot be calculated. So delta U is also not to be calculated, because U2 minus U1 can never be calculated exactly. But we have done at the expense of work and heat being performed, and that we have constituted as the first law of thermodynamics. So if U cannot be calculated exactly, something which is dependent upon U, that is enthalpy, how it can be calculated exactly? So similarly, enthalpy cannot be calculated exactly because internal energy cannot be calculated exactly, and it is dependent upon each other. So due to which we cannot have the exact value of enthalpy. Similarly, like internal energy, we will get the change in enthalpy of whatever kind of process goes on. Clear? So enthalpy is also constituted in some other way, where the constant volume constraints for the heat were put for the internal energy. Constant pressure is being stated for enthalpy. That we say for constant pressure reactions, the heat that is gained or lost by the reaction is called as enthalpy. Fine. As we stated in the internal energy course, we said that at constant volume, whatever heat is gained or lost by the system is called as change in internal energy. Similarly, at constant pressure, the other definition for enthalpy goes is that at constant pressure, the gain or loss of heat during a chemical reaction is called as enthalpy. Fine. Where we say that delta H is equal to delta E plus W, where W is P delta V. Fine. We haven't written H is equal to E plus PV. That is because we cannot calculate the exact E, neither the exact H. That's why we have delta H is equal to delta E, and W has been constituted as P delta V. Clear? In most all reactions, at atmospheric pressure, the work factor P delta V is very small compared to the internal energy change delta E. This may be very small with respect to this, and therefore, in most cases, delta H and delta E are practically the same value. If system is almost in the closest to the equilibrium of the surroundings, or the condition of the system before coming to the equilibrium with the surrounding is similar to that of surrounding, so not much of work is required to be done by the system to come in equilibrium with the surroundings. So in those cases, delta H and delta U of that very system are going to be same. But this is not a necessary condition. It may or may not be. But there are a lot of reactions where delta H and delta U goes equal because of the infinitesimal amount of work to be done by the system to come in equilibrium with the surroundings. Next slide, please. Clear? Okay. Now, the other relationship, the mathematical relationships we are actually going to use up because they are very necessary for the numerical purposes, where delta H and delta U are being related as the heat change at constant pressure for enthalpy and heat change at constant volume for internal energy. Fine. So P delta V is equal to P V2 minus V1 if the expansion is happening from a smaller volume V1 to bigger volume V2. So it will be final minus initial. If I off the brackets, it would be PV2 minus PV1, and the formula becomes where the formula is delta H is equal to delta U plus P delta V, which can be constituted as, because I say PV2 minus PV1, I'm assuming that gas inside the system is an ideal gas. So using an ideal gas equation, PV is equal to nRT, I can constitute PV1 equal to nRT, where it's an isothermal condition, so temperature is kept to be constant. So N2 RT. N2 is the number of moles at the final condition, and N1 are the number of moles at the initial condition. N2 RT minus N1 RT, because PV is equal to nRT. Fine. N2 minus N1, RT has been taken as common, and N2 minus N1, since the gas equation has been constituted over here, we have actually taken the gaseous molecules only. So the number of moles constituting here are of the gaseous state because of the ideal gas equation. So that is why we say that N2 minus N1, that means the final volume, final number of moles minus the initial number of moles is delta N, which constitute only the gaseous particles. Only ideal gas condition has been constituted. That means I have only calculated the gaseous molecules. We haven't taken into consideration of the liquid, aqueous, or maybe the solid particles. So these molecules are only the gaseous state. So that's why the G subscript has been given, where the gaseous reactants and gaseous products have been given to the N2 and N1. So delta H, where the P delta V has been constituted as delta NGRT, can be written as delta H is equal to delta U plus delta NGRT, where delta H is equal to QP, the heat transfer at constant pressure, and delta U is equal to heat transfer at constant volume plus delta NGRT, which can be used for the numerical purposes. Now, for the decomposition of calcium carbonate, this is an example we are just brushing up through. For the decomposition of calcium carbonate to calcium oxide and carbon dioxide, what is the difference between delta E and delta H value at 25 degrees centigrade? 25 degrees centigrade means 273 Kelvin plus 25 degrees centigrade equal to 298 Kelvin. Conversion happens this way. And 1 atmosphere. We know the reaction goes this way, where CO2 is in gaseous state, calcium oxide and calcium carbonate is in solid state. So solution goes that delta H can be calculated using the Hess's law, which we will be taking up in the next session of chemical thermochemistry. And delta H reaction comes up from this very aspect. This has been used by the thermochemistry, which will be taken up in the next time session. Delta H is equal to delta E plus P delta V because of the initial reaction we already have, where P delta V is equal to delta N RT. Therefore, delta H is equal to delta E plus P delta N RT, where delta E is just mathematically manipulated, where delta nRT has been taken to the other side, and we have written delta E is equal to delta H minus delta nRT, where delta N is the moles of gaseous products minus moles of gaseous reactant. In this very reaction, we have one carbon dioxide molecule, 1 mole of carbon dioxide on the product side, and no gaseous product on the reactant side. So it would be 1 minus 0. Delta Ng would be 1. Delta E is delta H, which has been calculated from the thermochemistry Hess's law. Delta H minus 1 into R. R value has been constituted, whose unit goes as decameter cube atmosphere per Kelvin per mole, into 25 plus 273, total constituting as Kelvin 298, comes up to be 569 kilojoules. Fine. So this is how we move with any kind of this formula to be used in a numerical. Next slide, please. Clear? Now, some more questions to brush you up with. If delta H is a change in enthalpy and delta U is the change in internal energy accompanying a gaseous reaction, then because the reaction goes as delta H equal to delta U plus delta Ng RT. That means what is the relation between delta H and delta U? Which one is going to be bigger? Because this comes up when something is added in internal energy. So internal energy cannot be greater than delta H until something is added to it. So delta H is always going to be greater than delta U if there are some gaseous product minus reactant is going to be a positive quantity. Else it will give a negative sign. If more number of reactant molecules are there in the gaseous state than the product side, then it's going to be a negative quantity, because delta N is number of product gaseous molecule minus number of reactant gaseous molecules. So that also ought to have a positive sign to have delta H as a domination over delta U. Fine. So let's pick and choose. A, delta H is always greater than U. Not true. Delta H is less than delta U only if number of moles of product is greater than the number of moles of reactant. Delta H is always less than U. Delta H is less than delta U only if number of moles of product is less than number of moles of reactants. So the option D goes only when delta H can only be lesser than delta U only if this is a negative sign. Because if we are subtracting something from the delta U, then it is coming equivalent to delta H. That means delta U is big enough than delta H. And subtraction will happen only if delta Ng is coming out as a negative value. And negative value will be when number of reactant gaseous molecules will be greater than the number of product gaseous molecules. Clear? Next question. The difference between the heats of reaction at constant pressure at constant volume at 25 degrees centigrade. 25 degrees centigrade means 298 Kelvin. For the reaction 2C6H6 in liquid condition plus 15 O2 gaseous condition goes to 12 CO2 gaseous conditions plus 6H2O in liquid form. So the difference between the heat of reaction at constant pressure and heat of reaction at constant volume is to be found. Now this is heat of reaction at constant pressure, which coins for the enthalpy change. This is heat of reaction at constant volume. The rest of the part remains the same. For a particular reaction, we need to calculate delta Ng. On the product side, there are 12 CO2. Water is in the liquid state, so we are not going to consider that. 12 number of moles of carbon dioxide on product side. On the reactant side, 15 for oxygen. Benzene is liquid, so we are not going to consider that as well. 12 minus 15, minus 3. Delta Ng is going to be minus 3. So Qp is equal to Qv minus 3 RT. The difference between the heats of reaction at constant pressure and constant temperature. That means it's asking for that Qp minus Qv. If I take this value over here, it will be Qp minus Qv. That will be minus 3 RT. Substituting the value of R and T. R is a gas constant which has a value 8.314 joule per Kelvin per mole. Minus 3 into 8.314 joule per Kelvin per mole into temperature. Since it has been mentioned that it's 25 degrees centigrade, so it goes to 298 Kelvin. When we multiply and get the answer, it comes out to be minus 7.43. So here we have the first option. Clear? As soon as I actually calculate my delta Ng, I very well get to know that sign of my option. So obviously option D and B will get striked out because of having the positive values. So I'm only left with the A and C. Now I have to come with the magnitude. So I will be calculating it using the formula. Clear? Next slide, please. Now measurement of delta U and delta H. As delta U is equal to heat at constant volume, to determine delta U, the heat change is determined when the reaction or the process is carried out in a closed vessel, because volume has to be constant. If it's not closed, so it cannot be kept constant. Fine. So example for such a reaction is bomb calorimeter. And delta H is equal to heat at constant pressure. So heat change determined when the reaction is carried out in an open vessel. Open vessel because pressure cannot change. If I keep on changing the heat inside the system, it will actually change the pressure. So better to have an open system so that the pressure do not change. How much amount of heat or I may give, because that open system will keep on transferring it to the surroundings, so pressure won't vary. Because my constraint for this is that pressure should be constant. So this should be an open system. However, for the volume constraint, I should have a closed system. Else, my condition for a constant volume won't come true. And for pressure constant condition, I have to have an open system. Clear? In both the above cases, the formula used is delta U or delta H is equal to C delta T by capital M, where M stands for the molecular mass by mass. Fine. Now, in bomb calorimeter, obviously, I will be using it as a closed system. So it will be delta U I am actually taking into consideration. If there is an open system I am constituting for, it will be delta H I will be calculating using the same formula and parameters. Clear? Okay, so I need to make sure that what kind of system I am having. If it is a closed system, I will be calculating delta U. If it's an open system, I will be calculating delta H. Now, delta Ng, I have already mentioned, is the difference between the number of gaseous products minus number of reactant products. If Np and Nr are same, that means number of gaseous products and number of reactant products are same. So delta Ng would go to 0. In that condition, delta H goes to delta U. Since this goes to 0, because delta Ng goes to 0, so this whole will become 0 and delta H becomes equal to delta U under those conditions. Now, for a cyclic process, what is a cyclic process? Any process which follows a cycle and comes back to the original position. Original position means if I started from here and I completed a cycle and I came back again to the original position, my final and initial positions are same. So there is no change in the initial and the final condition. In such case, all the state functions where they depend upon the final and the initial state would be zero variables. Like delta U, it's a state function. It depends upon the initial and the final state. Delta U is the final internal energy minus initial internal energy. Since both are met at the same place, the final condition and the initial place is same. So delta U would be 0. Similarly, the delta H, that is enthalpy at the final position, is same as the initial position because both the positions are same. So delta H will be 0. Clear? Now, during the isothermal expansion of an ideal gas, delta U is equal to 0 and delta T equals to 0 because it's an isothermal condition. Isothermal. So, ought to have delta T equal to 0. In later slides, I'll tell you that delta U is equal to Cv delta T. So since delta T equal to 0, so delta U also comes out to be 0. This relationship we will study in the later slide. But why delta U coming out to be 0? Because delta T is 0 and it is dependent directly upon the delta T. If that goes 0, delta U itself goes to 0. Thus, it is an isoenthalpic process. Fine. How isoenthalpic? Because this actually during an adiabatic expansion of real gas, Joule-Thomson effect is isoenthalpic. Isoenthalpic because enthalpy also goes as delta H equals to Cp delta T. So under those conditions, this also goes to 0. So delta H also goes to 0. As I say, isothermal means same temperature. That means delta T equals to 0. If I have delta H equal to 0, that means iso means same. Enthalpic means enthalpy. Everywhere enthalpy is same. That is constant. So the term isoenthalpic means delta H equal to 0. Fine. Understood? Okay. Next please. And this happens in the Joule-Thomson effect. Now, with some questions. The amount of heat measured for a reaction in a bomb calorimeter. Now, first of all, remember, bomb calorimeter we just studied is what kind of a system? Whether it is an open, closed or an isolated, closed. So, bomb calorimeter, bomb term has been given because of the closed thing only, else the reaction won't actually splurt out. Fine, just to remember it. So, the amount of heat measured for a reaction in a bomb calorimeter, what do we need to measure? In a closed system, internal energy change. We just stated. So we will study which option is the correct answer. C. That is delta U. For closed system, we always find out the delta U. For open system, we find out delta H. Since bomb calorimeter is an example of a closed system, we will find out delta U. The next question. At constant temperature and pressure, which of the following statement is correct for the reaction? At constant temperature and pressure, we say T is constant, P is constant. So, we need not to get confused with this because it has to, now looking at the options, it's actually stating the relationships between delta U and delta H. So, that means we are not at all going to be bothered with the temperature and pressure. That must be for the creating a kind of a confusion. We need to go with the relationship of delta H is equal to delta U plus delta Ng RT. Now delta H is equal to delta U plus delta Ng RT. For that I need to count on the delta Ng value. Here there is 1 mole of carbon monoxide in the reactant state and half a mole of oxygen as well. However, on the product side, it's only 1 mole of carbon dioxide on the product side. So in total, N2 would be 1, N1 would be 1 plus half, that will be 3 by 2. So 1 minus 3 by 2 is 1 minus 3 by 2 is, or you can say 1 plus half is 1 and a half. This is half, not to get confused. This is 1 and a half. This is half. 1 minus 1 and a half is minus half. So it is a negative value. If this goes negative because of 0.5 value of RT or 1 by 2 value of RT, what is the option which is best suited for this kind of a relationship? Since we have to subtract something from delta U to become equivalent to delta H, that means delta U is bigger than delta H. So which option goes correct? C. We are subtracting something from the delta U, then it's becoming equivalent to delta H. So that means delta U is bigger than delta H. Clear? So there may be some terminologies, though you need to read each and every word in the answers in an MCQ, but don't get confused, because when they're looking at the options, you know it very, very clearly it has nothing to do with T and P conditions, rather delta and G conditions. So just go back to your gaseous molecules, the number of moles of gaseous molecules in the reactants and the product side. That is what are you going to be bothered about to find the correct answer. Clear? Next, please. Now, the next terminologies we have is heat capacity. Heat capacity is the amount of heat needed to raise the unit amount of substance by a unit temperature. You must have been provided with some notes where it has been written that heat capacity is the amount of heat required to raise the temperature by 1 degree centigrade. Fine. However, specific heat capacity is the amount of heat required to raise the temperature by 1 degree centigrade of 1 gram of the substance. Fine. However, the molar heat capacity becomes the amount of heat required to raise the temperature by 1 degree centigrade for 1 mole of a substance. So the specific goes for the quantity to be mentioned. The term specific or the molar means to actually mention the quantity, how much quantity. Fine. So this heating can be carried out at a constant volume or constant pressure. I can actually create such conditions where I raise the temperature of the substance by 1 degree centigrade for 1 gram of a molecule, maybe at constant volume conditions or at constant pressure conditions. At constant pressure, some of the heat supplied goes to the doing work of expansion and less is available with the system. Fine. Did you understand? Let me cite an example for this. For example, I have a system in which there is a gas, an ideal gas, whose pressure, volume and temperature has P, T and V value. Fine. For example, I have to find out the heat capacity of this system. If I have to find out the heat capacity, that means the amount of heat required to raise the temperature of this system, which has maybe 1 gram of amount in total, by 1 degree centigrade. If I do so under constant volume condition, what happens? I provide the heat from the outside, since the wall is not adiabatic, but I'm constricting to the condition of constant volume. Isochoric condition. Volume should not change. That means my piston should not move outside, neither to inside. There are a lot of gas molecules inside. As soon as I provide heat from the surroundings, they will actually attain some kinetic energy and start moving faster. and start colliding, raising the temperature. Since I'm bound not to move the piston outward to keep the condition of delta V equal to 0 constant, temperature will actually rise very quickly because of the constrained constant volume. So whatever heat has been given is actually only giving rise to transfer of 1 degree of rise in temperature. Clear? However, when the same reaction is being brought about in the another condition, when constant pressure condition is to be maintained, that means no pressure should change. Now I am not bothered whether the volume constraint change or not. The only criteria I need to take into consideration is that pressure should not change. If pressure should not change, I am absolutely free to move the piston inward or outward, whatever happens, but pressure should not change. Means when I heat from the outside, what happens? The particles inside attain some kinetic energy. They start colliding with each other. They start colliding with the walls of the piston, pushing the piston outside. Now I'm not in a constraint of keeping the piston solid there itself. So it may move it outside. It will push it outside. Also to maintain the pressure same inside, because collision will actually rise the pressure. But now I have a constraint to keep the pressure constant. So in doing so, I ought to push the piston outside. Expansion is to be done to maintain the pressure constant inside. But that heat has been actually taken up in the expansion. The work is being done in the expansion work. So heat has not been attained by the gas molecules to raise the temperature by 1 degree centigrade. It has been used up or utilized for the expansion work. So some more amount of heat is required. Now, whatever other heat is being given, that will raise the temperature. So here, two things are being done, the expansion as well as the heating. However, when there was a constraint of delta V, it was only heating being taken up. So where is the more amount of heat required? In this case or this case, where only heating is required, or heating as well as expansion is required? Obviously, in the second case, more amount of heat is required because there are two jobs to be done. One is expansion, the other one is the heating of by 1 degree centigrade. The rise in temperature should be brought by 1 degree centigrade. Here, only temperature is to be brought at increase of 1 degree centigrade. So lesser amount of heat is required to do so. However, here two jobs are being done. So always the amount of heat required under constant pressure conditions would be greater. And the amount of heat required to raise the temperature by 1 degree centigrade for 1 gram of a substance at constant volume condition will be lesser than at constant pressure. Clear? Now understood? So now we read it again. This heating, addition of energy, can be carried out at constant volume or constant pressure. At constant pressure, some of the heat supplied goes into doing work of expansion. It's not heating it right now. It's doing the expansion work. And less is available with the system. So some more amount is required to actually increase the temperature by 1 degree centigrade. So that is why it is called as Cp at constant pressure. And at constant volume, it is called Cv. It is the slope of the plot of internal energy with temperature. Internal energy with temperature. We will come up with this mathematical expression also. We'll derive how did it come. And Cp is the slope of the plot of enthalpy with temperature. Since it's at constant pressure, it's the slope of a plot of enthalpy with temperature at constant pressure. Right? Units are going to be joule per Kelvin per mole, because it is the amount of heat required to raise the temperature by means per Kelvin. Kelvin by of 1 mole per mole of a substance. Joule per Kelvin per mole or degree centigrade. This is the SI unit. Rest are in the CGS forms. Heat capacity is an extensive property, because if the amount changes, if I extract out some amount of gas, so obviously less amount of heat is required to raise the temperature by 1 degree centigrade. So it is varying because of the amount of the substance inside. system's amount is being changed, the variable is changing. So this is an extensive property. It depends upon the amount of the matter. If substance has a higher heat capacity, then more heat is added to raise the temperature by 1 degree centigrade. If I say some substance has a higher heat capacity, that means it requires large amount of heat to raise the temperature by 1 degree centigrade. For example, water has higher heat capacity than the air in the atmosphere. That means to heat the air outside, less amount of heat is required. Rather, to heat the oceans, lot of heat is required. So whenever in summers, what happens? The air gets heated up first and then the ocean. You may find it's very hot outside, but still the ocean water is really cold. That is because of the higher heat capacity of the water than the atmospheric gas. So higher is the heat capacity, larger is the amount of heat required to raise the temperature by 1 degree centigrade. Getting it? Okay. As temperature goes to 0 Kelvin, the heat capacity tends to 0. Near 0 Kelvin, very little heat is required to raise the temperature of the sample. If something is at 0 temperature, 0 Kelvin temperature, very little amount of heat is required to raise the temperature by 1 degree centigrade. Always remember. That is why it is always said that whenever it's a bad news for cooling, because whenever you have your refrigerators, we always say that please shut it off, else there will be some melting happening, because it is very easy to actually melt down the 0 Kelvin temperature by raising the temperature. Very little amount of heat is required at near 0 Kelvin. This is an extra information I am giving you because these kinds of information has been asked in the entrance exams. Fine. So these are the applicative parts of the specific heats. So that is why we say that cooling to very low temperature, if a small leakage of heat will lead to a drastic increase of the temperature, because very less amount of heat is required to raise the temperature by 1 degree centigrade. So a large amount of heat may raise the temperature by multiple values of temperature. Clear? Next, please. So now we talk about the mathematical part of the heat capacities. Heat capacity at constant volume is said as Cv, where V is the subscript for the constant volume condition. Heat capacity at constant pressure is Cp, where P is for the pressure conditions. Now, according to the first law of thermodynamics, del Q, change in heat, is equal to del, this is for the delta. We write the small d, the complete small d. Del U plus PdV. PdV is the work done. Fine. Since this is the work of expansion, when we bring it out here, negative sign absorbs as a positive sign. The first law of thermodynamics is delta U is equal to del Q plus W. W is negative P delta. We expansion work. When brought here, this side, it becomes plus PdV. Fine. So C is equal to amount of heat required. This is del Q, amount of heat required. Amount of heat required to raise the temperature by 1 degree centigrade, where at constant volume we say dV is equal to 0. That means PdV goes to 0. At constant volume condition dV is equal to 0. So the above term dV goes to 0. In such condition, we are only left with du by dt under constant volume. So we say Cv, that is the heat capacity at constant volume, is du by dt at constant volume. Clear? This is for ideal gas. However, at constant pressure, neither this goes to 0 nor this one goes to 0. This is du plus pdv, which is itself enthalpy, dH. du plus pdv is enthalpy. So this becomes dH at dt under constant pressure conditions. So we have, combining the two, Cp is equal to dH by dt at constant pressure conditions. So under constant pressure conditions, Y it scales the slope of the enthalpy and temperature, and at under constant volume condition, it scales the slope of the internal energy and temperature. Understood well? Okay. Next slide, please. Now, relationship between Cp and Cv. Since Cp is the amount of heat required to raise the temperature by 1 degree centigrade at constant pressure condition, which comprise of the work to raise the temperature, heat to raise the temperature plus expansion done during that. and the amount of heat required, that is Cv, at constant volume condition only comprise of the heat required to raise the temperature by 1 degree centigrade. No expansion is required. So where is the more heat required? Under the Cp conditions. So this implies for the Cp, this implies for the Cv. Under Cp condition, more heat is required. So the amount of Cp is always going to be higher than the Cv. Because there are two kinds of jobs need to be done by those heat. That is the increase in the temperature by 1 Kelvin or 1 degree centigrade. Fine. Alongside, expansion is also happening. So larger amount of heat is required since the heat capacity is the amount of heat required. So Cp will be greater. However, Cv is the that heat only which actually needs to be required for the increase in the temperature. Fine. So that very case, we say that H is equal to, so always Cp is going to be greater than Cv. One thing. Another way around, we can also prove it again. H is equal to U plus PV. Clear? PV for an ideal gas can be substituted for 1 mole of a gas to RT. Since N is taken as 1, I say U plus RT for 1 mole of an ideal gas. dH by dt, integrating both the, differentiating both the sides with temperature. dH by dt is equal to du by dt plus R by dt by dt. That will cancel up. We'll be left with R only. So that means dH by dt is equal to du by dt plus R, where this is Cp, this is Cv and R. If we are adding something in Cv to come it equivalent to Cp, that means Cp is greater than Cv. We have to add something to Cv so that it becomes equivalent to Cp. That means Cp is greater than Cv. Only then only it will come equivalent. So Cp minus Cv is R, or you can say Cp is greater than Cv. The other way around, mathematically we have also proved. The conceptually also we have proved that it is the work of expansion plus work amount of heat required to raise the temperature, which actually is comprised in Cp. However, in Cv it's only the amount of heat required to raise the temperature by 1 degree centigrade in Cv. Fine. So both conditions, but what amount is the difference? That is R, by the amount of R. The Cp is greater than Cv by the gas constant R, that is approximately 2 calories or 8.314 joule, because 8.314 joule means 1 calorie is equal to 4.18 joule. So 8.3 must be around approximately 2 calories. Fine. So 2 calories of difference is there in Cp and Cv, where Cp is greater than Cv. For n moles, it will be Cp minus Cv. Remember, we had assumed n to be 1. Had it be n some value, it would be Cp minus Cv is equal to nR. And ratio is termed as gamma, which coins, because Cp is greater, we put it on the numerator. So gamma is always going to have a positive value. Positive, which is having a 1 or greater value. Greater than 1 value, because Cp is always greater than Cv. So it is always going to be greater than 1 and a positive value, because numerator is in the Cp for the Cp. So Cp is greater than Cv. So it's going to be greater than 1. The ratio Cp by Cv represented by gamma is related atomicity of the gas as follows. Because we know that for the gases, gamma is going to be monatomic gas Cp. How it comes up is, for a monatomic gas, Cp is equal to 5 by 2R. Cv is equal to 3 by 2R. This you must have studied in your gases. You have calculated it as well. For diatomic, 3 by 2 becomes 5 by 2R. And Cp is greater by the factor of R. If I add R to Cv, I get 5 by 2 plus 1, that comes out to be 7 by 2 R, and so on. So when I get the gamma, it is going to be equivalent to, for monatomic gas, 5 by 2 by 3 by 2, that is equal to 5 by 3. And similarly, it's going to be 7 by 5 for diatomic gases. So it's going to be 1.66 for monatomic, 1.40 for diatomic, and it keeps on decreasing as the number of atomicity keeps on increasing. Next slide. Next slide, please. Now the second law of thermodynamics. No, next. पीछे वाली. Second law of thermodynamics says, it is impossible to build a cycle machine that converts heat into work with 100% efficiency. What we are coining here, let's look at the diagrams over here. It says that 100% conversion of heat into work is not possible. This is not possible that 100% work comes up, because it says where as the heat is transferred to work in the form of engine, some is converted to the surroundings, the colder surroundings outside. Like for example, when you actually heat water on the gas burner, what happens? You provide 100 joules of heat to the container. Some of the heat is lost to the atmosphere by heating the air around the flame. Some is actually transferred to the vessel. The container is heated up, which is not transferred to the amount of work being done. If I am actually cooking my vegetables or I am making tea, the work is not being done. Whatever amount has been given has been lost to the surroundings as well. So 100% transfer of heat to work is not feasible. Next slide, please. This is what is being coined in second law of thermodynamics. Now, why it is not happening? That is because of the course of entropy. Entropy is the measure of disorderliness. Now, what is disorderliness? Right? I am actually throwing some coins from the side of the desk. It is very unlikely that all the coins actually come and spontaneously actually come up in a heap, one upon another. Rather, the more realistic manner would be that they will just fall off like anything. So this is because of the entropy. Randomness is there. There is no ordered system. So this is the reason that 100% heat cannot be converted into 100% work, because it actually loses up to the surroundings, or you can say the randomness is increasing. Next slide, please. Now the entropy, the natural direction of all change in towards increase of entropy is that the state of matter with the greatest entropy is gas, because gas particles are very far apart. Fine. So the degree of randomness is very much there. They can move randomly as much as they want. Liquids, what happens? They are more compactly placed as the gaseous molecules. Now they cannot move as randomly as gaseous molecules. So degree of randomness is less. So the randomness or the entropy will be less for the liquids than gases. And the least will be for the solids, because they are tightly packed solids. They cannot move here or there. So randomness won't happen. They are absolutely placed where they should be. So randomness is not there. They are all ordered. So the least entropy would be for the solids. Fine. The next comes is the only substance having a perfectly ordered state is zero entropy. When entropy is zero, only that is called as the perfectly ordered state. And that perfectly ordered state happens in a perfect crystal, a solid, at absolute zero temperature, because you know, as you increase the temperature, the lattice spaces are actually start moving because of the gain in the terms of kinetic energy. So we say that lowering down the temperature to 0 Kelvin for a perfectly crystalline solid, entropy is 0 Kelvin. That coins for the third law of the thermodynamics. Fine. This is the third law of thermodynamics. Only then the randomness would be 0. Perfectly crystalline, absolutely true, but temperature should also be brought to 0 Kelvin, because raising the temperature, molecules will start getting the kinetic energy, they will start moving, so randomness will occur. So 0 Kelvin temperature actually lowers the entropy factor again. So 0 entropy will only happen when there is a perfectly crystalline solid at 0 Kelvin temperature. These conditions can never be met, therefore all substances have some innate entropy or randomness. In realistic world, all substances have some entropy the other, because both the conditions cannot be met in reality, just like ideal gases do not exist. Fine. From an entropy standpoint, reactions tend to progress towards the formation of gaseous form from liquids and solids, and also tend towards decomposition, forming more molecules from fewer, thereby being capable of an even greater disordered condition. What it means that if I say that randomness is increasing, it's only when a solid state like ice is converting into water. Now molecules are farther than they were in the ice state. So the entropy has increased from solid to liquid state. Then when I actually vaporize them in the water vapor form, again, the molecules have actually moved farther. So randomness is, there is more space for the more randomness. So entropy has further actually increased. So entropy may increase if I change the phase from solid to liquid, liquid to gaseous. But it changes further if the gas molecules, water molecules, H2O, break up and decompose into H2 and O2. Because now there are more number of molecules moving randomly. The number of molecules have actually increased. It was only one H2O molecule moving randomly, which was coining for randomness, which were actually accounting for entropy. Now there are two more instead of one. It's H and it's H2 and it's oxygen. So because of that, more random molecule will be there. So decomposition lead to further randomness. So state from solid to liquid, liquid to gas actually increases the entropy, but decomposition further increases, or number of increase in the molecules or number of increase of the atoms would actually further increase the entropy. Next slide, please. Fine. So both the factors are to be taken into consideration when coining for entropy. Entropy is symbolized with the alphabet capital S. Entropy change can be defined as the heat absorbed by the system divided by the Kelvin temperature at which the heat is added. So delta S, entropy change, this is again a state function. Delta S is the amount of heat absorbed by the system divided by the temperature. At what temperature the heat was absorbed. Fine. That is why the unit becomes joule for heat divided by Kelvin. So joule per Kelvin. Unlike enthalpy and internal energy, which are pure energy states, which have SI units as joule. Here it will be joule per Kelvin because it is heat divided by temperature. Fine. The change in entropy for a chemical reaction can be calculated by delta S equal to summation of all the products. All the products, like for example, ABC is giving rise to CDE. So summation of entropy of CDE plus summation of minus summation of all the entropies of ABC. Fine. This will give you the delta S. Clear? Entropy values from reactants and products can be obtained from the thermodynamic tables, which are already been mentioned in the numerical purposes. It will be mentioned always. Available entropy values are referred as standard values, those measured at 25 degrees centigrade and 1 atmosphere gas pressure. So standard values means, because you know, varying the temperature value, the variable may change. So standard conditions means that temperature is 25 degrees centigrade, that is 298 Kelvin, and atmospheric pressure is 1 atmosphere. Fine. It is the standard condition, and under those conditions, the entropy values of lot of crystalline and rest of the elements, they have been coined in form of a data which may be used for the numerical purpose. Next slide, please. When the standard condition comes, S has a standard subscript over it as naught. So it is going to be S as naught. This naught comprises of the standard state. It may be on the enthalpy as well. Enthalpy under standard state, that means when there is a 25 degrees centigrade of temperature and 1 atmospheric pressure, the calculation has been created at the standard state. Next slide, please. Yeah. But I have to complete few. Just let's come up with. Okay, I will. But I'll just need to finish it up. Now it's not finished yet. Okay, next slide. Entropy change. During process is defined as the amount of change. Entropy change, I have told you, it's a reversible process in heat divided by the temperature. Fine. Now unit, I have already mentioned CGS, it will be Kelvin, calorie per Kelvin per mole. Entropy change during a phase transformation is taken up by the heat, and heat has been transformed in the form of total heat is enthalpy of that very process, enthalpy of fusion, enthalpy of vaporization, or enthalpy of sublimation. Yes, next. calculation of delta S at standard state for a reaction. Like for example, there is a problem. Delta has been given for different reactions. Now the reaction is carbon dioxide, water and carbon monoxide, water and carbon dioxide and ammonia actually are being formed. So there is a data being given. What you have to do, sum the total entropy of all the reactants and subtract the total entropy of reactants from the products. Fine. You will get the value of the entropy. Clear? Since it is a positive quantity, that means there is a large entropy in this kind of a reaction. Next. We'll be quick with this, then we'll take up. There are few questions to brush you up with this. Which of the following processes will lead to increase in the entropy of the system? Now you have to see if gaseous molecules are converting into gaseous, there may not be entropy change. But if the molecules, number of molecules are increasing, there is 4 leading to 2. So, but product minus reactant, how many are actually coming up? Fine. So this is not leading to a increase in the entropy. However, liquid to gaseous state, there is an increase in the entropy. Here, it's solid converting into gaseous. So again, there is an increase in the entropy. Here, solid liquid is converting into aqueous. No increase in the entropy. Clear? So the increase in the entropy will be in the second option as well as in the third. Fine? Next, please. Oh, wait. The enthalpy of vaporization of water is 186.5 kilojoule per mole. The entropy of its vaporization would be, since enthalpy of vaporization is 186.5, you know vaporization of water happens at 100 degrees centigrade. That will be 373 Kelvin. And entropy change would be delta H by T. So it will be 186.5 divided by 373. And that will come up to be 0.5 kilojoule per Kelvin per mole. So option A is to be strike for that. This is how you calculate. Next, which of the following is true for the reaction? Liquid water is converting into gas. It is an interconvertible reaction at 100 degrees centigrade at 1 atmosphere. Is delta S equal to 0 for such reaction? Delta H equal to 0 for such reaction? Whether delta H is equal to delta U for such reaction or delta H is equal to T delta S for such reaction. It's going to be D. Fine. Because what we say, delta H, it's a phase transformation reaction. So delta S formulate as delta H by T. So we can just cross multiply and take this term over here. So this relation becomes feasible. Because for phase transformation, I had just quoted delta S is equal to delta H by T. So just cross multiplying the temperature over here to this side becomes this equation. So D option is the correct. Next. Enthalpy and entropy of the reaction spontaneity. When system react and entropy increases, a natural tendency based on the second law of thermodynamics happens that energy is absorbed. According to the first law of reaction, tend to towards lowest energy state, that they tend to release energy. How can we tell that what will really occur when these two opposing tendencies drive reaction? Now we say the spontaneity actually happen at the two cases, that is with the increase in the energy and with the increase in the entropy, and because you know all fast reactions have very higher range of randomness, so there must be increase in the entropy. But what in terms of the energy? Helmholtz equation, it relates the enthalpy factor and entropy factor, both which are driven reaction spontaneity. Spontaneity, reconciling these driving forces resulted in term is called as Gibbs free energy. The Gibbs free energy delta G, this allows us to decide the net effect on the entropy and enthalpy on the chemical reaction and predict spontaneity. Because next, both the factors enthalpy and entropy coin for the spontaneity, which gives a term called delta G, gives free energy, which is this. Delta G is equal to delta H minus T delta H. Delta S also coined for the spontaneity, delta H, because of the first and second law of thermodynamics also comprise for the spontaneity. So we say that delta S for a reaction is positive, the reaction is favored and entropy is increasing. because fast reactions have higher entropy. If you ride a car at a very faster pace, there tend to be a lot of randomness, but reaction will be rapid. If you move slowly, you will be very cautious. You won't be moving randomly. You will be following all the rules, all the red lights, abide by the road traffic rules and everything. So the faster reactions or the spontaneous reactions tend to have higher entropy, higher degree of randomness. Delta H is negative. The reaction is favored by enthalpy decreasing. Delta H going to be negative, that means it's an exothermic reaction. All reactions which are exothermic are going to be fast. If you have to give energy, so reaction will wait and won't happen until you provide energy. But exothermic reaction need not to wait. It will just start up because it will release energy. It is not actually abide by anybody. So it's going to be spontaneous. So delta H going to negative is a spontaneous reaction. So delta G having delta H negative minus T delta S going to be positive will give you negative sign. So that is why we say that delta G is negative sign is a spontaneity sign. It shows that reaction is spontaneous. The next slide. If delta H is positive, that is endothermic reaction. We know that endothermic reactions are very slow. They are actually very much constrained until the energy is provided. They cannot take place. So they cannot be the spontaneous reaction. So the reaction is not favored by enthalpy changes. And if the entropy is negative, that means the degree of randomness is very less. It's negative. That product is having very less randomness than the reactant. It is more random, more regular now, less disordered. That means delta S is negative. So reaction is not favored. So reaction is not having any spontaneity. So delta G would have plus sign for delta H minus plus sign for temperature and negative sign for delta S. So it will have a negative delta G if there is plus sign and this is greater. But it will only have negative sign only when this is having this is going to be a positive sign because negative and negative will make it positive. So this will become positive. This will have a positive sign. This is a mistake written over here. Just make a correction because positive minus positive into negative. This will be negative. Negative into negative will be positive. So there will be a positive sign for delta G. If delta G is positive, the reaction will be non-spontaneous, or you will say, next please, will be plot. Delta G is 0 only when there is an equilibrium reaction. Fine. So the conditions can be coined. You can see that delta G positive for forward reaction is non-spontaneous. It's written other way around. Fine. Delta G is negative for a spontaneous reaction. Delta G is positive for a non-spontaneous reaction, and delta G goes to 0 for equilibrium reactions. Fine. Where delta H is equal to T delta S. Clear? For equilibrium conditions. Next slide, please. Now let's solve a problem. In this reaction, N2 is a gas, O2 is a gas, goes to 2NO gaseous reaction. From the data we have delta H of NO gas and delta S naught has been given for NO and N2 and as well as for O2. So we find out the delta S of the reaction using the formula of summation of products of entropy minus summation of reactant of entropy. Using with the stoichiometric coefficient because product have two NO molecules, 2 into the NO molecule entropy minus summation of the nitrogen and oxygen entropies. Total will be the delta S naught. Enthalpy has been already been given by the Hess's law of heat summation, which will be taken up in the next session of thermochemistry. Delta G is delta H minus T because this reaction has been brought up at 25 degrees centigrade, 298 Kelvin into delta S, which is 592 calories per Kelvin, T delta S. So the answer for delta G comes out to be a positive. So this reaction is a non-spontaneous reaction. Next. Now, deciding on the reaction spontaneity without calculating. In the previous question, we had calculated and then found out that the sign is coming out to be positive. How to do that? Since in this kind of a reaction, delta H is coined as negative. So we know that this is a kind of an exothermic reaction. Now, here two liquid molecules are giving rise to two liquid molecules along with the gaseous molecule. So degree of randomness is also increasing because liquids are changing into the gaseous state. So both there, what happens that delta H is negative and delta S is positive. because here the more randomness is because of the gaseous state and less randomness because of the liquid state. So products are having a greater value of delta S than the reactant. So delta S is positive. So this is a spontaneous reaction. Next, please. If we comprise of a condition, because we have delta G is equal to delta H minus T delta S, we can create different conditions where we say that where delta H is negative and delta S is positive, delta G is shortly going to be negative, so it's going to be a spontaneous reaction. And when delta H is positive or delta S is negative, the other way around, it's going to be a non-spontaneous reaction. However, when delta H is and delta S have same signs both sides, then it depends whether it's going to be positive or negative depending upon the factor of the T delta S, whether it is dominating the negative sign and leading to delta G coming out to be as a resultant to be negative, then the reaction would be spontaneous or not. Now, let's brush up with this. For a reaction A to B, delta H and delta S are positive. Both are positive. The most favorable condition of the reaction is, what should be the condition? Because we say that delta G should be negative, which is delta H minus T delta S. For reaction to be spontaneous, this should be negative. But we say this is also positive, this is also positive. What should be the value of the temperature? Obviously, we need to have a negative value, so this should be greater than this value to have delta G equal to be negative. That means this is positive, so this value should be really higher value. So that condition should be high temperature. Obviously, concentration and rest of the parameters do not really depend on, so we need not to bother for them. A spontaneous reaction is impossible if, I just coined, if delta H is positive and delta S is negative. Fine. However, delta H is positive, delta S is negative. We had just actually talked off. So C option is correct for here. If this goes positive and this goes negative, because negative make it positive and this is positive term. So in total, delta is going to be positive, delta is going to be negative. This will be positive, positive into negative will be negative, and negative will make positive. So delta G will be positive. So in turn, it will give a non-spontaneous reaction. So option C is correct. If an endothermic reaction is non-spontaneous at freezing point means low temperature of water and becomes feasible at boiling point, means high temperature. Then that means if temperature is low, reaction is non-spontaneous. If temperature is high, reaction becomes spontaneous. So what should be the condition? Both are positive, because if both are positive at lower temperature, this does not dominate delta H at the freezing condition, and hence this is positive. So it is a non-spontaneous reaction. However, other way around, when temperature is raised to the boiling temperature, this dominates the value of delta H and hence becomes delta G equal to negative. Reaction becomes spontaneous. Next slide. Free energy and equilibrium. Now, the state where we say that delta G is at equilibrium, then we say equilibrium delta G is equal to 0. So that we have a reaction condition, we have a formula whose derivation is not in your syllabus. Delta G is equal to delta G naught, delta G at standard state, plus RT ln Q. Q is nothing but the ratio of product to reactants, the concentration of product to reactants. If we are considering thing at the equilibrium, delta G goes to 0. So that this very formula becomes, this goes to 0. Delta G naught is equal, this becomes 0 is equal to delta G naught plus RT ln K. Ln K is nothing but Q. Fine. So here it becomes ln K is equated as ln Q, which is K is the equilibrium constant, concentration of products over concentration of reactant. We take it out here, we get a generate a negative sign. So we have delta G naught is equal to minus RT ln K. Free energy and equilibrium, we have one problem to solve here. Just let's see. This is the reaction we need to solve for. Delta G for SO2 in the reactant has been given, for the product has also been given. We'll find out the delta G naught, which can be done by the summation of product minus summation of the reactant. Stoichiometric 2 into minus 370 minus 2 into 300 gives minus 140. Delta G naught is minus 140. we know is a gas constant. T, the temperature has been actually put up for the RT ln K. Ln K is minus delta G by RT, where ln K is minus 140 into 10 raised to power 3 for conversion of kilojoule to joule divided by 8.314 R and 298 Kelvin. When the temperature is never given in the numerical like this one, you ought to take the standard condition, because you always know that this delta G naught is at a standard state. So that means temperature must be 298 Kelvin. It's not mentioned. You should be knowing that it's a standard state. So it's 298. Answer comes out to be 56.56. It is ln. You need to take anti-log of it. It will be giving you the answer. Next, please. Now, what are coupled reactions? Coupled reactions are when A plus B goes to C plus D, whose delta G value is very, very positive. That means a non-spontaneous reaction is occurring. Then we have another reaction and we club the two reaction. Another reaction D plus C going to F and G, where the G2 is really highly negative. Because when we actually club the reaction or couple the reaction, what will happen? The delta G will also couple and will give you an effect that delta G1 plus delta G2 will become negative. Fine. So the you can say resultant answer would be that delta G would be negative. So reactions are coupled in order to make them spontaneous. So any non-spontaneous reaction is coupled with a very highly spontaneous reaction so as to make the resultant reaction spontaneous. So this completes the course of thermodynamics. Now we take up some online questions. Q and delta Q. There is a huge difference between Q and delta Q. Like I said, delta term means final minus initial condition. These are the subnotations used for the state functions. However, del is used for the path functions. Both of them actually give you the reason for the final minus initial condition, but it is a notation being used for the state function, that is delta. We cannot use the del for the state functions. For path functions, delta cannot be used because it is not depending upon the final and the initial conditions. So we are constrained to use the delta function in terms of del functions. So actually the meaning is same, that is for the variation of final minus initial, but path functions cannot be used the delta. That's why we use del term for them. Next question. Why pH and EMF of a cell are intensive property? EMF is not an intensive property, it's an extensive property because it depends upon the concentration. However, pH is. Because we say, if there is a bucket of water where there is a not water, acid, we constrain some amount of pH paper and we figure out that the pH of HCl or maybe citric acid pH comes out to be 2. If we take out 10 ml of citric acid from here, still the pH would be 2 because the amount of concentration of H plus has been removed, but that volume has also been taken into consideration. So that is uniform. Just for example, it does not matter whether you take the pH of a full bucket of HCl of pH 2 or a one maybe 100 ml quantity of HCl. The pH would be same. It won't differ because the concentration of hydrogen ion is uniform all over. So if you extract out here, the concentration of hydrogen ion of here is the same as the whole of the solution. So pH remains the same whether the quantity changes or not. So it's an intensive quantity. However, EMF, according to the Nernst equation, this is dependent upon the concentration of products over reactants. So this is not an intensive quantity. I also had mentioned then that it is an extensive quantity. However, the option wasn't mentioned so. Third, how we can remember sign convention. I just mentioned for the sign convention, for the heat release, always remember global warming is a negative aspect, heat release happens with a negative aspect. So release will be always negative. If the other way around, heat is absorbed, the effect of global warming goes down. So it's a positive aspect. If you treat your system as a guest, you know in our culture in India, we do not allow guests to work. To remember the sign convention, work done by the system is just like work done by the guest. So it's a negative thing. So work done by the system is negative, work done on the system is positive. Why? If work is done, temperature is increased, then how Q will be zero in a closed system? Q is not zero. Its change in Q is zero. There is no transfer of Q in the zero. Temperature is a quantity which has not to be confused with heat. It is absolutely different. By the virtue of temperature, heat transfer happens. Because of the difference of the temperature, heat transfer happens. But it is absolutely not heat. And Q is not zero, change in heat. That means transfer of heat does not happen. Why EMF of a cell is not an extensive property? EMF of a cell is an extensive property. I just mentioned EMF of a cell is an extensive property. It was that it was not mentioned in any of the options. For the question we had that EMF had an option. It had, I guess, 4th or 5th. Can we just point out on the slide number 4th or 5th we have? आगे चलिए, चलते जाइए, आगे आगे आगे, रुको 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 रुको, आगे, इससे नेक्स्ट आगे. Let's repeat again. EMF was at number 4 and none of the options had number 4. That's why we did not strike any of the options but for the option none. Though we mentioned that molar heat capacity and EMF are extensive quantities, extensive with change with the amount of the substance. However, the first three, boiling point, viscosity and pH, do not change with the amount of the quantity being transferred. But the option 4 and 5 has not been mentioned together in any of the 4 options. That's why we answered none. Next question, please. Why enthalpy is extensive property? Enthalpy is extensive property because enthalpy is the amount of heat required, that is in the sum of internal energy and the amount of heat required to come in equilibrium with the surroundings. So if we say that enthalpy is nothing but it's, you can say, for example, there is a system where n number of moles are actually having some internal energy, alongside they are coming in equilibrium with the surroundings. So in that very case, enthalpy will be having some. However, if I take out some amount out of it, there will be a different enthalpy because of the fewer number of the quantity of molecules. The enthalpy change for a reaction zinc plus 2H gives zinc plus H2 is this much. The formation of 2 gram of hydrogen expands the system by 22.4 liter at 1 atmosphere. What will be the internal energy change in the reaction? Formation of 2 grams expands by system. The formation of 2 gram of H expands the system. Now for this we need to use the formula delta H is equal to delta U plus P delta V, where the delta V expanded by 22.4, the enthalpy change. 1 atmosphere, 2 grams. The formation of 2 grams of hydrogen expands the system by 22.4. By using the formula, delta H is equal to delta U plus P delta V, where the enthalpy change for reaction enthalpy is minus 1544 kilojoule per mole is equal to delta U is to be found out plus P delta V. The formation of 2 grams of hydrogen expands the system by 22.4 liter at 1 atmosphere. This is at standard state, 22.4 liter by 1 atmosphere. So we can actually revert this formula to, because it's a gaseous state, we can have delta H equal to delta U plus delta Ng RT. Since you know that for liquids at standard state, the volume goes to 22.4 liter. So that means the standard state atmospheric conditions are, pressure is already been mentioned as 1 atmosphere. Your temperature condition ought to be of the standard condition, that will be 298 Kelvin. You will put delta H equal to minus 1544 kilojoule per mole. Delta U you have to find out. Delta Ng you will calculate by calculating the number of gaseous moles being changed. R is the gas constant, 8.314. You can substitute that. T will be the temperature of the standard case, because here it has been stated that the expansion of the volume has been considered to the standard state, that is 22.4 liter at 1 atmosphere. So the condition goes to the temperature of the standard state 298, and you can find out the value. Next, in the delta S equation, what is the meaning of reversible Q? Reversible Q is the amount of heat released or absorbed during a reversible reaction. It's just that means that the reaction, this delta S is pertaining to the reversible reactions. So Q tends to the reversible processes. Is solidification of a liquid not an example of process of decreasing entropy? Absolutely, it is an example of solidification of liquid, is also termed as fusion, but it is an example of decrease of entropy, because as we move from solid to liquid, liquid to gas, entropy tend to increase. If we move other way around from gases to liquid, liquid to solid, entropy decreases. So that's absolutely an example of decrease of entropy. Next. That's it. Thank you very much.